On a monitor in a cosmology office, the universe does not look like a dome of stars. It looks like a map covered with faint points, colored pixels, and curves that have been fitted through data. Each point is a galaxy or a quasar. Each curve is an attempt to describe how space itself has been stretching while the light was on its way to us. Somewhere inside those measurements is a question that sounds simple only because the words are small. Will the universe end by fading, by tearing itself apart, or by continuing into a darkness with no clear final moment? The image on the screen may have come from a telescope on a mountain, from a spacecraft that scanned the afterglow of the early universe, or from a survey that measured the positions of millions of galaxies. It is not a photograph of the future. No telescope can take that. It is a record of the past, turned carefully into a model, and then extended beyond every direct observation humans have ever made. Cosmology is built on this kind of restraint. Astronomers do not watch galaxies move away in real time the way you might watch a boat drift from shore. They measure redshift, brightness, angular size, gravitational lensing, the faint texture of the cosmic microwave background, and the way galaxies gather in long filaments across enormous distances. Then, they ask which universe could have produced all of those traces at once. The answer, at least for now, is unsettling because it is incomplete. The universe is expanding. That much is built into modern cosmology. The expansion is accelerating. That has been supported by supernovae, cosmic background measurements, galaxy surveys, and other independent lines of evidence. But the cause of that acceleration is still given a placeholder name: dark energy. Until dark energy is understood, the final fate of the universe remains open. The end of the universe is not a single image. It could be a long cooling, where galaxies become isolated islands and stars eventually stop forming. It could be a big rip if the acceleration strengthens until even bound systems cannot remain bound. It could be an endless dark future, not dramatic in any ordinary sense, but so long that black holes and particles become the last remaining markers of change. These possibilities are not ancient myths moved into scientific language. They come from equations, observations, and uncertainties. The same cosmic expansion that carries distant galaxies away also tells scientists something about the ingredients of the universe. The same background radiation that shows the universe as it was when it became transparent also helps constrain what it may become. The future is hidden, but it is not disconnected from evidence. If the quiet fate of the universe is the kind of mystery that brings you here, subscribing keeps the next long journey close. The question now is how to follow a universe into a future that cannot be photographed. The only way is to begin with what can be measured. A star has a lifetime because its fuel is finite. A galaxy has a history because its stars, gas, dust, and dark matter change over time. A black hole has a temperature in quantum theory, though for most of cosmic history it is far colder than the radiation around it. Even darkness has a physics to it. The universe is 13.8 billion years old, but that number is not the scale of the story. It is only the opening fraction. If the Big Freeze is right, the future is not merely longer than the past. It is longer by factors that make the age of stars, planets, and galaxies seem brief. If the Big Rip is right, the universe may have a final clock. If dark energy changes in some unexpected way, even the familiar choices may not be the whole map. The first clue is everywhere and almost invisible. It is in the fact that distant galaxies are redder than nearby ones. Not because all of them are old or dusty, but because the wavelengths of their light have been stretched while space expanded. A spectral line that should appear at one color appears shifted toward another. That shift is not decorative. It is a ruler, a clock, and a warning that the universe is not standing still. A redshift measurement is a modest thing on a page. It might be a number beside the name of a galaxy in a catalog. It might be a peak in a spectrum, a line of hydrogen displaced from where it would appear in a laboratory on Earth. But when thousands and then millions of those measurements are arranged together, they reveal a universe in motion, with more distant galaxies generally receding faster because the space between us has grown. That discovery changed the question of cosmic fate. A static universe can simply be old. An expanding universe has a direction. It was denser and hotter in the past. It may be thinner and colder in the future. Once expansion becomes part of the evidence, the end of the universe is no longer only a philosophical idea. It becomes a problem in physics. What is in the universe? How does it gravitate? And how does the rate of expansion change with time? The difficulty is that the universe does not contain only the matter we can see. Stars, planets, gas clouds, dust lanes, comets, moons, and living bodies are made of ordinary matter. But ordinary matter is a small fraction of the total cosmic budget. Dark matter is inferred from gravity, from galaxy rotation, from lensing, from the growth of structure. Dark energy is inferred from expansion. Both are real in their effects, but neither is directly visible as a familiar substance. A galaxy cluster bending the light of background galaxies into arcs is a physical scene, not just a diagram. The cluster contains hot gas glowing in X-rays, galaxies filled with stars, dark matter arranged in a broad halo, and space-time curved enough to distort light. When scientists model that lensing, they find more gravity than the visible material provides. The same habit of inference, cautious and mathematical, is used when dark energy enters the story. For the fate of the universe, dark energy matters more than almost anything else. If it behaves like a cosmological constant, the expansion will keep accelerating in a steady way. Galaxies beyond the local gravitational neighborhood will gradually cross horizons of observation and influence. Star formation will decline. The universe will cool. The Big Freeze becomes the most straightforward future. If dark energy evolves, the future may be different. The word end can be misleading here. The Big Freeze is not a wall. There is no final explosion. There is no instant when every clock stops. It is more like the slow exhaustion of all useful differences. Hot things cool. Dense regions are separated by expanding space. Stars run through their fuel. White dwarfs dim. Black holes become the last great reservoirs of mass. The universe continues, but fewer and fewer processes remain capable of doing work. The Big Rip is harsher because it has a different assumption at its core. If dark energy becomes stronger as the universe expands, then acceleration can grow without limit. Galaxies would first lose sight of one another. Later, galaxy clusters, galaxies, stars, planets, and perhaps even atoms would be unable to remain bound. This is not the favored ordinary picture under the simplest model, but it is one reason scientists measure dark energy so carefully. Endless darkness is a quieter phrase, but in many ways it is the most difficult to imagine correctly. It does not mean empty space in the simple sense. It means a future after ordinary starlight has become rare, after the cosmic microwave background has been stretched to wavelengths so long and energies so low that it no longer resembles the microwave background we detect today, after galaxies are no longer connected by reachable light. To understand those futures, the story has to move through what the universe is doing now, what it has already done, and what the evidence allows scientists to say. The end of the universe is not decided by fear or preference. It is written, if it is written at all, in expansion rates, energy densities, particle physics, stellar evolution, black hole thermodynamics, and the still unfinished nature of dark energy. Before any scenario can be taken seriously, the expansion itself has to be earned. That means returning to the instruments, a spectrograph splitting galaxy light into lines, a supernova light curve measured over weeks, a sky map of microwave radiation built from years of scanning, a survey field where thousands of fibers take spectra from distant targets at once. The end of the universe begins, oddly, with patient bookkeeping. A Type 1a supernova appears in a distant galaxy. Its light curve rises and fades in a way that lets astronomers estimate its true brightness. When it looks dimmer than expected, it becomes evidence for cosmic acceleration. That is how a question as large as the fate of the universe becomes something specific enough to test. A measurement is made, checked against other measurements, and placed inside a model that can succeed or fail. This is why the instruments matter so much. A faint signal can be mistaken for noise, foreground dust can imitate something more distant, and a calibration error can move a conclusion by more than anyone wants. Modern cosmology is strong not because it avoids these problems, but because it names them and tries to make independent methods meet in the same physical picture. Consider a cosmic microwave background sky map filled with tiny temperature differences. Those differences are only fractions of a degree, but they preserve the early distribution of matter and radiation. This is not just another detail for a catalog. This helps fix the age, geometry, and composition of the universe, and that single fact becomes part of the larger attempt to understand whether the universe is fading, tearing, or continuing into a darker equilibrium. No single measurement carries the whole future. A supernova can be affected by dust. A spectrum can be limited by signal to noise. A galaxy map can be shaped by selection effects. The pattern becomes convincing only when different tools, with different weaknesses, keep pointing toward the same expansion history. One part of the evidence is simple to state. A galaxy survey measures baryon acoustic oscillations. The pattern is the fossil scale of sound waves that moved through the hot early plasma. When that fact is placed beside redshift, structure, temperature, and time, it works like a standard ruler stretched across cosmic time. The universe becomes readable only by combining many kinds of faint evidence. The data may look ordinary at first: columns of numbers, uncertainties, filters, exposure times, redshifts, but those ordinary records are the only bridge between human time and cosmic time. The universe does not announce its fate. It leaves small measurable changes in light, and those changes have to be protected from every easier explanation. A researcher working with this evidence is not seeing the end directly. The future is absent from the frame. What is present is a constraint. A weak lensing map is built from faint distortions in galaxy shapes, and each galaxy has been blurred and sheared by gravity along the path of its light. From that constraint, the combined pattern reveals how matter has clumped while the universe expanded. The conclusion remains careful because the measurement is indirect. This is why the instruments matter so much. A faint signal can be mistaken for noise, foreground dust can imitate something more distant, and a calibration error can move a conclusion by more than anyone wants. Modern cosmology is strong not because it avoids these problems, but because it names them and tries to make independent methods meet in the same physical picture. At first, the fact that a quasar spectrum carries absorption lines from gas clouds between the quasar and Earth may not seem like a statement about cosmic endings. Each line marks material at a different redshift. The whole spectrum becomes a layered record of the expanding cosmic web. Nothing in cosmology stands alone for long. Every reliable statement has to survive contact with the rest of the sky. No single measurement carries the whole future. A supernova can be affected by dust. A spectrum can be limited by signal to noise. A galaxy map can be shaped by selection effects. The pattern becomes convincing only when different tools, with different weaknesses, keep pointing toward the same expansion history. The physical picture begins here. An infrared telescope sees galaxies whose light has been stretched far beyond visible wavelengths. The color is not just appearance, but travel time and expansion written into the photons. That picture matters because it shows that the oldest frames become tests of how structure grew. It keeps the question close to matter, radiation, gravity, and time, where an ending can be discussed without pretending the unknown is already solved. The data may look ordinary at first: columns of numbers, uncertainties, filters, exposure times, redshifts, but those ordinary records are the only bridge between human time and cosmic time. The universe does not announce its fate. It leaves small, measurable changes in light, and those changes have to be protected from every easier explanation. A supercomputer simulation begins with tiny fluctuations and lets gravity work. Dark matter collapses into filaments, while gas falls into halos where stars can form. The result is compared with real galaxy maps rather than accepted on faith. That is how a question as large as the fate of the universe becomes something specific enough to test. A measurement is made, checked against other measurements, and placed inside a model that can succeed or fail. This is why the instruments matter so much. A faint signal can be mistaken for noise, foreground dust can imitate something more distant, and a calibration error can move a conclusion by more than anyone wants. Modern cosmology is strong not because it avoids these problems, but because it names them and tries to make independent methods meet in the same physical picture. Consider this. A radio telescope measures the 21-centimeter line from neutral hydrogen. The signal is faint and easily buried under foreground emission. This is not just another detail for a catalog. It may one day reveal how ordinary matter filled the Dark Ages and later structures, and that single fact becomes part of the larger attempt to understand whether the universe is fading, tearing, or continuing into a darker equilibrium. No single measurement carries the whole future. A supernova can be affected by dust. A spectrum can be limited by signal to noise. A galaxy map can be shaped by selection effects. The pattern becomes convincing only when different tools, with different weaknesses, keep pointing toward the same expansion history. One part of the evidence is simple to state. A table of redshifts looks dry until it is plotted. Then, nearby galaxies, distant galaxies, and quasars separate into a pattern of recession and history. When that fact is placed beside redshift, structure, temperature, and time, the data turn distance into a story of changing expansion. The universe becomes readable only by combining many kinds of faint evidence. The data may look ordinary at first: columns of numbers, uncertainties, filters, exposure times, redshifts, but those ordinary records are the only bridge between human time and cosmic time. The universe does not announce its fate. It leaves small, measurable changes in light, and those changes have to be protected from every easier explanation. A researcher working with this evidence is not seeing the end directly. The future is absent from the frame. What is present is a constraint. A telescope mirror has collected photons that left before the solar system existed, and those photons arrive mixed with noise, cosmic rays, detector artifacts, and foreground dust. From that constraint, careful calibration is part of the science, not a technical afterthought. The conclusion remains careful because the measurement is indirect. This is why the instruments matter so much. A faint signal can be mistaken for noise, foreground dust can imitate something more distant, and a calibration error can move a conclusion by more than anyone wants. Modern cosmology is strong not because it avoids these problems, but because it names them and tries to make independent methods meet in the same physical picture. The fate of the universe depends on its contents, but contents in cosmology do not mean only objects. They mean energy density, pressure, curvature, radiation, matter, and the rules that tell space-time how to respond. A planet and a photon are contents. A dark matter halo is a content. Dark energy, whatever it physically is, behaves like a content because it changes the expansion. Consider this: ordinary matter forms the stars, planets, gas clouds, meteorites, and dust that telescopes can see. It carries chemistry and light. This is not just another detail for a catalog. It accounts for only a small part of the cosmic energy budget, and that single fact becomes part of the larger attempt to understand whether the universe is fading, tearing, or continuing into a darker equilibrium. This balance between what is visible and what is inferred keeps the fate question open. Ordinary matter can be photographed, weighed in stars, analyzed in spectra, and sampled in meteorites. Dark matter and dark energy are known through their effects. They shape the largest answer while remaining unlike any material that can be placed in a laboratory jar. One part of the evidence is simple to state: Dark matter gathers around galaxies in halos. It does not shine in ordinary telescopes. When that fact is placed beside redshift, structure, temperature, and time, its presence is inferred from gravity acting on stars, gas, lensing arcs, and the cosmic web. The universe becomes readable only by combining many kinds of faint evidence. The visible universe is therefore not the whole dynamical universe. A galaxy's stars show only part of its mass. A cluster's hot gas shows only part of its gravity. The expansion history shows a component that does not behave like ordinary matter at all. The ending depends on the invisible as much as on the visible. A researcher working with this evidence is not seeing the end directly. The future is absent from the frame. What is present is a constraint. Dark energy is not a glowing fluid in a photograph, and it is a name for whatever drives the observed accelerated expansion. From that constraint, its simplicity in equations hides how little is known about its physical nature. The conclusion remains careful because the measurement is indirect. This does not make cosmology vague. It makes it indirect. Gravity, light, motion, and statistics become the tools for weighing things that cannot be seen directly. The same indirect method that reveals dark matter also frames the question of dark energy. The point sounds local. The cosmic web stretches across hundreds of millions of light years. Galaxy clusters sit at knots, filaments connect them, and voids open between them. The large-scale structure records the competition between gravity and expansion. Nothing in cosmology stands alone for long. Every reliable statement has to survive contact with the rest of the sky. This balance between what is visible and what is inferred keeps the fate question open. Ordinary matter can be photographed, weighed in stars, analyzed in spectra, and sampled in meteorites. Dark matter and dark energy are known through their effects. They shape the largest answer while remaining unlike any material that can be placed in a laboratory jar. The physical picture begins here. The local group remains gravitationally bound. The Milky Way, Andromeda, and smaller galaxies are not being pulled apart by cosmic expansion. That picture matters because it shows that local gravity still defeats expansion on small enough scales. It keeps the question close to matter, radiation, gravity, and time, where an ending can be discussed without pretending the unknown is already solved. The visible universe is therefore not the whole dynamical universe. A galaxy's stars show only part of its mass. A cluster's hot gas shows only part of its gravity. The expansion history shows a component that does not behave like ordinary matter at all. The ending depends on the invisible as much as on the visible. Beyond the local neighborhood, galaxies are increasingly carried away by expanding space. The most distant ones already show light from ancient epochs rather than current conditions. The future will make that separation more severe. That is how a question as large as the fate of the universe becomes something specific enough to test. A measurement is made, checked against other measurements, and placed inside a model that can succeed or fail. This does not make cosmology vague. It makes it indirect. Gravity, light, motion, and statistics become the tools for weighing things that cannot be seen directly. The same indirect method that reveals dark matter also frames the question of dark energy. Consider this: a galaxy is not a single object in the simple sense. It is a system of stars, gas, dust, black holes, dark matter, magnetic fields, and past collisions. This is not just another detail for a catalog. Its future depends on all of those components and on the expansion outside it, and that single fact becomes part of the larger attempt to understand whether the universe is fading, tearing, or continuing into a darker equilibrium. This balance between what is visible and what is inferred keeps the fate question open. Ordinary matter can be photographed, weighed in stars, analyzed in spectra, and sampled in meteorites. Dark matter and dark energy are known through their effects. They shape the largest answer while remaining unlike any material that can be placed in a laboratory jar. One part of the evidence is simple to state: galaxy clusters contain hot gas that glows in X-rays. The gas is hotter and more massive than the visible stars in many cases. When that fact is placed beside redshift, structure, temperature, and time, its pressure and distribution help measure the gravity of the cluster. The universe becomes readable only by combining many kinds of faint evidence. The visible universe is therefore not the whole dynamical universe. A galaxy's stars show only part of its mass. A cluster's hot gas shows only part of its gravity. The expansion history shows a component that does not behave like ordinary matter at all. The ending depends on the invisible as much as on the visible. A researcher working with this evidence is not seeing the end directly. The future is absent from the frame. What is present is a constraint. The cosmic microwave background is nearly uniform, and the tiny departures from uniformity are the seeds of later structure. From that constraint, without those differences, galaxies would have had no clear starting pattern. The conclusion remains careful because the measurement is indirect. This does not make cosmology vague. It makes it indirect. Gravity, light, motion, and statistics become the tools for weighing things that cannot be seen directly. The same indirect method that reveals dark matter also frames the question of dark energy. Begin with the plain fact that the Hubble constant describes the present expansion rate. Different methods have produced a tension in the exact value. That tension reminds scientists that precision can reveal unresolved physics as well as measurement difficulty. Nothing in cosmology stands alone for long. Every reliable statement has to survive contact with the rest of the sky. This balance between what is visible and what is inferred keeps the fate question open. Ordinary matter can be photographed, weighed in stars, analyzed in spectra, and sampled in meteorites. Dark matter and dark energy are known through their effects. They shape the largest answer while remaining unlike any material that can be placed in a laboratory jar. The Big Freeze does not begin in a distant blackness. It begins inside stars that are shining now. Every main sequence star is converting hydrogen into helium, releasing energy because the products of fusion are slightly lighter than the ingredients. That missing mass becomes light and heat. The process feels stable from a human lifetime, but it is a reservoir being drained. One part of the evidence is simple to state: the sun will not last forever. Its core hydrogen is finite, and its later red giant phase will transform the inner solar system. When that fact is placed beside redshift, structure, temperature, and time, this local future is small compared with the fate of galaxies, but easier to picture. The universe becomes readable only by combining many kinds of faint evidence. This stage is still recognizably astrophysical. There are stars, disks, dust lanes, star clusters, supernova remnants, and planets lit by suns. The difference is statistical rather than sudden. Over immense time, the rate of new star formation falls. Long-lived stars become more important, and the universe slowly moves away from the brilliant period in which most familiar astronomy takes place. A researcher working with this evidence is not seeing the end directly. The future is absent from the frame. What is present is a constraint. Red dwarf stars burn fuel with extraordinary thrift, and their small masses keep their cores stable for times far longer than the current age of the universe. From that constraint, they will become some of the last ordinary stars still shining. The conclusion remains careful because the measurement is indirect. The change does not happen evenly. Some galaxies exhaust their gas early. Some continue forming stars for longer. Some receive new gas through mergers or streams. But the broad direction is the same. Fuel is finite, stellar lifetimes are finite, and the luminous era has a beginning and an end. On its own, massive stars are brief by cosmic standards seems like a narrow observation. They spend their fuel quickly and end as supernovae, neutron stars, or black holes. Their brilliance comes with short lifetimes. Nothing in cosmology stands alone for long. Every reliable statement has to survive contact with the rest of the sky. This is why the big freeze can begin while the universe still looks bright. The future is already present inside the fuel budgets of stars and galaxies. Every star forming now is part of a cycle that will not continue indefinitely. The physical picture begins here. White dwarfs are the exposed cores of stars like the Sun. They shine with leftover heat rather than active fusion. That picture matters because it shows that over immense times they cool toward black dwarfs that do not yet exist because the universe is too young. It keeps the question close to matter, radiation, gravity, and time, where an ending can be discussed without pretending the unknown is already solved. This stage is still recognizably astrophysical. There are stars, disks, dust lanes, star clusters, supernova remnants, and planets lit by suns. The difference is statistical rather than sudden. Over immense time, the rate of new star formation falls, long-lived stars become more important, and the universe slowly moves away from the brilliant period in which most familiar astronomy takes place. Neutron stars are compressed remnants from massive stellar cores. Their surfaces, magnetic fields, and densities are extreme. In the far future, they become isolated markers of earlier star formation. That is how a question as large as the fate of the universe becomes something specific enough to test. A measurement is made, checked against other measurements, and placed inside a model that can succeed or fail. The change does not happen evenly. Some galaxies exhaust their gas early, some continue forming stars for longer, some receive new gas through mergers or streams. But the broad direction is the same. Fuel is finite, stellar lifetimes are finite, and the luminous era has a beginning and an end. Consider this. Black holes form from collapsed stars and from the growth of galactic centers. They can gain mass by swallowing gas, stars, and other black holes. This is not just another detail for a catalog. In a frozen future, they may outlast nearly everything else that once shone, and that single fact becomes part of the larger attempt to understand whether the universe is fading, tearing, or continuing into a darker equilibrium. This is why the big freeze can begin while the universe still looks bright. The future is already present inside the fuel budgets of stars and galaxies. Every star forming now is part of a cycle that will not continue indefinitely. One part of the evidence is simple to state. Molecular clouds are the birthplaces of stars. They depend on cold gas gathering under gravity. When that fact is placed beside redshift, structure, temperature, and time, as galaxies consume or lose their gas, the raw material for new stars becomes less available. The universe becomes readable only by combining many kinds of faint evidence. This stage is still recognizably astrophysical. There are stars, disks, dust lanes, star clusters, supernova remnants, and planets lit by suns. The difference is statistical rather than sudden. Over immense time, the rate of new star formation falls, long-lived stars become more important, and the universe slowly moves away from the brilliant period in which most familiar astronomy takes place. A researcher working with this evidence is not seeing the end directly. The future is absent from the frame. What is present is a constraint. Supernovae seed future clouds with heavy elements, and the shock waves compress gas and can help trigger new star formation. From that constraint, when star formation declines, that recycling loop weakens. The conclusion remains careful because the measurement is indirect. The change does not happen evenly. Some galaxies exhaust their gas early. Some continue forming stars for longer. Some receive new gas through mergers or streams. But the broad direction is the same. Fuel is finite, stellar lifetimes are finite, and the luminous era has a beginning and an end. The chain includes even this. Brown dwarfs are failed stars that never sustain ordinary hydrogen fusion. They glow faintly with leftover heat and slowly cool. They may drift through the dark future as common but dim bodies. Nothing in cosmology stands alone for long. Every reliable statement has to survive contact with the rest of the sky. This is why the big freeze can begin while the universe still looks bright. The future is already present inside the fuel budgets of stars and galaxies. Every star forming now is part of a cycle that will not continue indefinitely. The physical picture begins here. Rogue planets may be ejected from their systems by gravitational encounters. They carry no sunrise with them. That picture matters because it shows that some may keep internal heat for long periods, but they do not change the larger cosmic outcome. It keeps the question close to matter: radiation, gravity, and time, where an ending can be discussed without pretending the unknown is already solved. This stage is still recognizably astrophysical. There are stars, disks, dust lanes, star clusters, supernova remnants, and planets lit by suns. The difference is statistical rather than sudden. Over immense time, the rate of new star formation falls, long-lived stars become more important, and the universe slowly moves away from the brilliant period in which most familiar astronomy takes place. Far beyond the age of the sun, beyond the merger of galaxies, beyond the last bright star forming clouds, the Big Freeze becomes less like astronomy as people usually picture it. It is no longer mainly about nebulae and spiral arms. It is about remnants, rare encounters, fading backgrounds, and the slow disappearance of usable energy differences across expanding space. A researcher working with this evidence is not seeing the end directly. The future is absent from the frame. What is present is a constraint. After the last bright stars fade, galaxies become collections of remnants, and white dwarfs, neutron stars, black holes, brown dwarfs, and planets remain. From that constraint, the familiar era of starlight has ended. The conclusion remains careful because the measurement is indirect. The language begins to fail because ordinary experience contains no comparison. 1,000,000 years can erase mountains on Earth. 1,000,000,000 years can reshape a biosphere. The intervals involved in the black hole era are so much longer that even the age of galaxies becomes an early episode. The story remains physical, but the scale resists imagination. At first, the fact that orbits inside old galaxies slowly change through repeated gravitational encounters may not seem like a statement about cosmic endings. Stars and remnants exchange energy over enormous times. Some objects are flung outward while others sink towards central black holes. Nothing in cosmology stands alone for long. Every reliable statement has to survive contact with the rest of the sky. There is no need to add spectacle to this future. Its severity comes from duration. Processes that look impossible from a human perspective become plausible when the clock is long enough. Stellar remnants scatter, orbits change, backgrounds cool, and even black holes may slowly lose mass. The physical picture begins here. The cosmic microwave background continues to stretch. Its photons lose energy as the universe expands. That picture matters because it shows that what is now a cold afterglow becomes colder and longer in wavelength. It keeps the question close to matter, radiation, gravity, and time, where an ending can be discussed without pretending the unknown is already solved. The universe at this stage is not busy in the way it is now. It is sparse, patient, and dominated by rare events. The fact that something can still happen does not mean the future is luminous or rich with structure. A future observer in a bound galaxy may see little evidence of other galaxies. Accelerated expansion will have carried most distant systems beyond practical observation. Cosmology itself could become harder to reconstruct. That is how a question as large as the fate of the universe becomes something specific enough to test. A measurement is made, checked against other measurements, and placed inside a model that can succeed or fail. The language begins to fail because ordinary experience contains no comparison. 1,000,000 years can erase mountains on Earth. 1,000,000,000 years can reshape a biosphere. The intervals involved in the black hole era are so much longer that even the age of galaxies becomes an early episode. The story remains physical, but the scale resists imagination. Consider this. Entropy increases as energy spreads into less useful forms. The Big Freeze is therefore a thermodynamic future as much as an astronomical one. This is not just another detail for a catalog. The important loss is not matter, but usable contrast, and that single fact becomes part of the larger attempt to understand whether the universe is fading, tearing, or continuing into a darker equilibrium. There is no need to add spectacle to this future. Its severity comes from duration. Processes that look impossible from a human perspective become plausible when the clock is long enough. Stellar remnants scatter, orbits change, backgrounds cool, and even black holes may slowly lose mass. One part of the evidence is simple to state: black holes are not perfectly black in quantum theory. Hawking radiation gives them a temperature and a possible way to lose mass. When that fact is placed beside redshift, structure, temperature, and time, for stellar and supermassive black holes, this process is unimaginably slow. The universe becomes readable only by combining many kinds of faint evidence. The universe at this stage is not busy in the way it is now. It is sparse, patient, and dominated by rare events. The fact that something can still happen does not mean the future is luminous or rich with structure. A researcher working with this evidence is not seeing the end directly. The future is absent from the frame. What is present is a constraint. The black hole era would be almost entirely dark, and large black holes would be among the last massive organized structures. From that constraint, their eventual evaporation belongs to timescales far beyond stellar history. The conclusion remains careful because the measurement is indirect. The language begins to fail because ordinary experience contains no comparison. 1,000,000 years can erase mountains on Earth. 1,000,000,000 years can reshape a biosphere. The intervals involved in the black hole era are so much longer that even the age of galaxies becomes an early episode. The story remains physical, but the scale resists imagination. The point sounds local. If protons decay, ordinary matter has another route toward disappearance. If they do not, remnants may persist much longer. Particle physics therefore enters the cosmic future in a direct way. Nothing in cosmology stands alone for long. Every reliable statement has to survive contact with the rest of the sky. There is no need to add spectacle to this future. Its severity comes from duration. Processes that look impossible from a human perspective become plausible when the clock is long enough. Stellar remnants scatter, orbits change, backgrounds cool, and even black holes may slowly lose mass. The physical picture begins here. The universe may keep expanding forever without ever reaching a final instant. Many processes approach zero without arriving there in ordinary time. That picture matters because it shows that an end can be an asymptote rather than an event. It keeps the question close to matter, radiation, gravity, and time, where an ending can be discussed without pretending the unknown is already solved. The universe at this stage is not busy in the way it is now. It is sparse, patient, and dominated by rare events. The fact that something can still happen does not mean the future is luminous or rich with structure. The last useful energy differences fade into a dilute background. Particles, radiation, and perhaps extremely cold remnants spread across expanding space. This is why heat death is also called a freeze. That is how a question as large as the fate of the universe becomes something specific enough to test. A measurement is made, checked against other measurements, and placed inside a model that can succeed or fail. The language begins to fail because ordinary experience contains no comparison. 1,000,000 years can erase mountains on Earth. 1,000,000,000 years can reshape a biosphere. The intervals involved in the black hole era are so much longer that even the age of galaxies becomes an early episode. The story remains physical, but the scale resists imagination. The Big Rip is different because it gives the universe a sharper kind of ending. It does not simply wait for stars to exhaust themselves. It asks whether the expansion of space could become strong enough to defeat every binding force in sequence. The answer depends on a hypothetical behavior of dark energy, and that condition matters because without it the scenario does not happen. Begin with a plain fact. The Big Rip begins with a change in the behavior of dark energy. its density would have to grow rather than remain constant or decline. That hypothetical form is often called phantom energy. Nothing in cosmology stands alone for long. Every reliable statement has to survive contact with the rest of the sky. The sequence matters because it keeps the scenario from becoming a simple disaster image. Galaxies are weakly bound compared with stars. Planetary systems are stronger. Atoms are stronger still. A big rip capable of reaching the smallest scales would have to pass through every larger scale first, and each stage would be controlled by the changing balance between expansion and binding. The physical picture begins here. A galaxy cluster is held together by gravity. Dark energy, under ordinary assumptions, does not tear it apart today. That picture matters because it shows that phantom energy would eventually make expansion stronger than binding. It keeps the question close to matter, radiation, gravity, and time, where an ending can be discussed without pretending the unknown is already solved. This is the reason the Big Rip is both vivid and conditional. Its effects are easy to describe once phantom energy is assumed, but that assumption has not been established. The scenario remains a serious branch of the map, not the main road under the simplest reading of current data. The first visible consequence would not be planets breaking. It would be the loss of distant cosmic structure from any shared horizon. The universe would become more isolated before it became physically disrupted. That is how a question as large as the fate of the universe becomes something specific enough to test. A measurement is made, checked against other measurements, and placed inside a model that can succeed or fail. The important question is not whether the phrase sounds dramatic. The important question is whether dark energy can have the required equation of state and keep it into the future. Without that behavior, galaxies can age and horizons can empty without the local universe being torn apart. Consider this. Galaxies would be separated, then gravitationally bound systems would fail. Stars would no longer remain in galactic orbits. This is not just another detail for a catalog. The familiar architecture of galaxies would dissolve, and that single fact becomes part of the larger attempt to understand whether the universe is fading, tearing, or continuing into a darker equilibrium. The sequence matters because it keeps the scenario from becoming a simple disaster image. Galaxies are weakly bound compared with stars. Planetary systems are stronger. Atoms are stronger still. A big rip capable of reaching the smallest scales would have to pass through every larger scale first, and each stage would be controlled by the changing balance between expansion and binding. One part of the evidence is simple to state. Solar systems would be vulnerable only much later. Planets are tightly bound compared with galaxies. When that fact is placed beside redshift, structure, temperature, and time, a big rip must become enormously stronger before it reaches that scale. The universe becomes readable only by combining many kinds of faint evidence. This is the reason the Big Rip is both vivid and conditional. Its effects are easy to describe once phantom energy is assumed, but that assumption has not been established. The scenario remains a serious branch of the map, not the main road under the simplest reading of current data. A researcher working with this evidence is not seeing the end directly. The future is absent from the frame. What is present is a constraint. Atoms are bound by electromagnetic forces, and they are much smaller and stronger than planetary systems. From that constraint, tearing them apart belongs to the final extreme version of the scenario. The conclusion remains careful because the measurement is indirect. The important question is not whether the phrase sounds dramatic. The important question is whether dark energy can have the required equation of state and keep it into the future. Without that behavior, galaxies can age and horizons can empty without the local universe being torn apart. On its own, the Big Rip is not currently the default conclusion. Seems like a narrow observation. It depends on dark energy, having properties that observations have not established. Its value is that it shows how deeply the future depends on one unknown component. Nothing in cosmology stands alone for long. Every reliable statement has to survive contact with the rest of the sky. The sequence matters because it keeps the scenario from becoming a simple disaster image. Galaxies are weakly bound compared with stars. Planetary systems are stronger. Atoms are stronger still. A big rip capable of reaching the smallest scales would have to pass through every larger scale first, and each stage would be controlled by the changing balance between expansion and binding. The physical picture begins here. A phantom energy universe has a finite future in many models. The scale factor grows without limit in a finite time. That picture matters because it shows that the mathematics gives a clock where the big freeze gives a fade. It keeps the question close to matter, radiation, gravity, and time, where an ending can be discussed without pretending the unknown is already solved. This is the reason the Big Rip is both vivid and conditional. Its effects are easy to describe once phantom energy is assumed, but that assumption has not been established. The scenario remains a serious branch of the map, not the main road under the simplest reading of current data. Current surveys try to measure the equation of state of dark energy. Small deviations from a cosmological constant would matter enormously. The future can change because of a parameter that is difficult to pin down. That is how a question as large as the fate of the universe becomes something specific enough to test. A measurement is made, checked against other measurements, and placed inside a model that can succeed or fail. The important question is not whether the phrase sounds dramatic. The important question is whether dark energy can have the required equation of state and keep it into the future. Without that behavior, galaxies can age and horizons can empty without the local universe being torn apart. Consider this. The phrase "rip" sounds violent. But the scientific question is precise. This is not just another detail for a catalog. Can expansion overcome the forces that bind structures? And if so, at what scale and when? And that single fact becomes part of the larger attempt to understand whether the universe is fading, tearing, or continuing into a darker equilibrium. The sequence matters because it keeps the scenario from becoming a simple disaster image. Galaxies are weakly bound compared with stars. Planetary systems are stronger. Atoms are stronger still. A big rip capable of reaching the smallest scales would have to pass through every larger scale first, and each stage would be controlled by the changing balance between expansion and binding. Recent dark energy measurements do not close the story. They make it more interesting. Large surveys are now mapping the expansion history with enough detail to ask whether dark energy is truly constant or whether its influence has changed. The simplest model still works remarkably well in many tests, but hints of tension are valuable because they tell observers where to look again. The physical picture begins here. New galaxy surveys have made dark energy less abstract. Millions of galaxy and quasar positions trace expansion across much of cosmic history. That picture matters because it shows that the data are large enough to test whether the simplest model is complete. It keeps the question close to matter, radiation, gravity, and time, where an ending can be discussed without pretending the unknown is already solved. A hint is not a discovery, and cosmologists know this better than almost anyone. Large datasets can contain subtle systematics. Different probes can pull in different directions for reasons that have nothing to do with new physics. Still, persistent tension is not ignored, because the history of astronomy contains many cases where careful disagreement became the doorway to a better model. Some recent results hint that dark energy may evolve. Taken alone, the evidence is not a final verdict. Combined datasets make the question more serious. That is how a question as large as the fate of the universe becomes something specific enough to test. A measurement is made, checked against other measurements, and placed inside a model that can succeed or fail. The alternative is not to believe every anomaly, it is to measure better. More galaxies, better calibration, longer baselines, cleaner lensing maps, and larger supernova samples can turn a hint into a result or dissolve it into error. Either outcome improves the map. Consider this: the cosmological constant is simple. It behaves as an energy density of space that does not dilute as space expands. This is not just another detail for a catalog. Its simplicity is one reason it remains powerful, and one reason any deviation would be important. And that single fact becomes part of the larger attempt to understand whether the universe is fading, tearing, or continuing into a darker equilibrium. This is the patient part of the mystery. The future of the universe may depend on a pattern too subtle to see without millions of galaxies and years of survey work. The scale is cosmic, but the progress is incremental. One part of the evidence is simple to state. Quintessence models imagine a dynamic field. The field could change over time or space. When that fact is placed beside redshift, structure, temperature, and time, such models can alter the far future without requiring the universe to tear apart. The universe becomes readable only by combining many kinds of faint evidence. A hint is not a discovery, and cosmologists know this better than almost anyone. Large datasets can contain subtle systematics. Different probes can pull in different directions for reasons that have nothing to do with new physics. Still, persistent tension is not ignored, because the history of astronomy contains many cases where careful disagreement became the doorway to a better model. A researcher working with this evidence is not seeing the end directly. The future is absent from the frame. What is present is a constraint. Modified gravity offers another route, and perhaps the equations of gravity need adjustment on the largest scales. From that constraint, that idea must still explain every success of general relativity on smaller and tested scales. The conclusion remains careful because the measurement is indirect. The alternative is not to believe every anomaly, it is to measure better. More galaxies, better calibration, longer baselines, cleaner lensing maps, and larger supernova samples can turn a hint into a result or dissolve it into error. Either outcome improves the map. The chain includes even this. A big crunch would require expansion to slow, stop, and reverse. Current evidence does not make that the standard expectation. Evolving dark energy keeps the wider family of outcomes scientifically interesting. Nothing in cosmology stands alone for long. Every reliable statement has to survive contact with the rest of the sky. This is the patient part of the mystery. The future of the universe may depend on a pattern too subtle to see without millions of galaxies and years of survey work. The scale is cosmic, but the progress is incremental. The physical picture begins here. Vacuum decay is another speculative possibility. A lower energy state of the vacuum could change physics itself. That picture matters because it shows that there is no evidence that such a transition is imminent or even possible in our universe. It keeps the question close to matter, radiation, gravity, and time, where an ending can be discussed without pretending the unknown is already solved. A hint is not a discovery, and cosmologists know this better than almost anyone. Large datasets can contain subtle systematics. Different probes can pull in different directions for reasons that have nothing to do with new physics. Still, persistent tension is not ignored, because the history of astronomy contains many cases where careful disagreement became the doorway to a better model. Cosmological horizons limit what can ever be known. Some regions are already beyond any signal that can reach us now. Future observations will still be powerful, but never omniscient. That is how a question as large as the fate of the universe becomes something specific enough to test. A measurement is made, checked against other measurements, and placed inside a model that can succeed or fail. The alternative is not to believe every anomaly. It is to measure better. More galaxies, better calibration, longer baselines, cleaner lensing maps, and larger supernova samples can turn a hint into a result or dissolve it into error. Either outcome improves the map. Consider this: Euclid, Roman, Rubin, and ground-based surveys are part of the same larger effort. They will map galaxies, lensing, supernovae, and structure with increasing precision. This is not just another detail for a catalog. The fate question is tied to that patient accumulation of data, and that single fact becomes part of the larger attempt to understand whether the universe is fading, tearing, or continuing into a darker equilibrium. This is the patient part of the mystery. The future of the universe may depend on a pattern too subtle to see without millions of galaxies and years of survey work. The scale is cosmic, but the progress is incremental. One part of the evidence is simple to state. The universe may be simple at large scales and still difficult to understand. A smooth acceleration can hide profound ignorance. When that fact is placed beside redshift, structure, temperature, and time, a good model is not the same thing as a complete explanation. The universe becomes readable only by combining many kinds of faint evidence. A hint is not a discovery, and cosmologists know this better than almost anyone. Large datasets can contain subtle systematics. Different probes can pull in different directions for reasons that have nothing to do with new physics. Still, persistent tension is not ignored, because the history of astronomy contains many cases where careful disagreement became the doorway to a better model. Endless darkness is not a separate universe from the Big Freeze. It is what the freeze can become when the luminous part of cosmic history is finished. The phrase is simple, but the physical process behind it is layered. Stars die, gas is used up, remnants cool, black holes dominate, radiation thins, and expansion continues carrying what remains farther apart. Darkness in the far future is not merely the absence of light, it is the loss of engines that make new light in the first place. Without fresh stars, the visible universe becomes an archive rather than a growing system. That is how a question as large as the fate of the universe becomes something specific enough to test. A measurement is made, checked against other measurements, and placed inside a model that can succeed or fail. Darkness here is a measurable condition. There are fewer photons with enough energy to warm surfaces, fewer stars to define skies, fewer collisions dense enough to ignite fusion, and fewer gradients that can power change. It is not a supernatural absence. It is the ordinary consequence of expansion, cooling, and exhaustion carried to an extreme. Consider this: a cold white dwarf drifts through an old galaxy. Its surface temperature falls over times longer than any current star has existed. This is not just another detail for a catalog. Eventually, it becomes a black dwarf in models of the far future, and that single fact becomes part of the larger attempt to understand whether the universe is fading, tearing, or continuing into a darker equilibrium. The phrase can sound absolute, but physics is often more careful than language. There may still be particles, radiation, and rare interactions. What disappears is the familiar brightness of organized astrophysical systems and the abundance of energy differences that make change common. One part of the evidence is simple to state: a planet without a star may continue moving through a galaxy for immense intervals. Internal heat, radioactive decay, and tidal history determine what little energy it has. When that fact is placed beside redshift, structure, temperature, and time, it is not a symbol, but a physical world with a cooling interior. The universe becomes readable only by combining many kinds of faint evidence. A dark future is not necessarily empty. It is a future where remaining matter and radiation are too cold, too thin, or too separated to rebuild the kind of luminous universe that exists now. A researcher working with this evidence is not seeing the end directly. The future is absent from the frame. What is present is a constraint. A neutron star can spin down slowly, and its magnetic field and radiation weaken. From that constraint, after long enough, it becomes harder to detect except by gravity or rare interactions. The conclusion remains careful because the measurement is indirect. Darkness here is a measurable condition. There are fewer photons with enough energy to warm surfaces, fewer stars to define skies, fewer collisions dense enough to ignite fusion, and fewer gradients that can power change. It is not a supernatural absence. It is the ordinary consequence of expansion, cooling, and exhaustion carried to an extreme. At first, the fact that collisions do not stop entirely may not seem like a statement about cosmic endings. Given enough time, rare encounters can occur between remnants. The far future is quiet, but not perfectly still. Nothing in cosmology stands alone for long. Every reliable statement has to survive contact with the rest of the sky. The phrase can sound absolute, but physics is often more careful than language. There may still be particles, radiation, and rare interactions. What disappears is the familiar brightness of organized astrophysical systems and the abundance of energy differences that make change common. The physical picture begins here. Old galaxies may lose many of their objects. Gravitational encounters can eject remnants into intergalactic space. That picture matters because it shows that the idea of a galaxy becomes less like a bright city and more like a sparse gravitational memory. It keeps the question close to matter, radiation, gravity, and time, where an ending can be discussed without pretending the unknown is already solved. A dark future is not necessarily empty. It is a future where remaining matter and radiation are too cold, too thin, or too separated to rebuild the kind of luminous universe that exists now. Central black holes can merge as galaxies merge. Gravitational waves carry energy away. In the very long future, fewer large structures remain available to merge. That is how a question as large as the fate of the universe becomes something specific enough to test. A measurement is made, checked against other measurements, and placed inside a model that can succeed or fail. Darkness here is a measurable condition. There are fewer photons with enough energy to warm surfaces, fewer stars to define skies, fewer collisions dense enough to ignite fusion, and fewer gradients that can power change. It is not a supernatural absence. It is the ordinary consequence of expansion, cooling, and exhaustion carried to an extreme. Consider this. The last photons from ordinary stars are stretched and thinned. They do not vanish at a boundary. This is not just another detail for a catalog. They become part of an expanding background too weak to mark familiar time, and that single fact becomes part of the larger attempt to understand whether the universe is fading, tearing, or continuing into a darker equilibrium. The phrase can sound absolute, but physics is often more careful than language. There may still be particles, radiation, and rare interactions. What disappears is the familiar brightness of organized astrophysical systems and the abundance of energy differences that make change common. One part of the evidence is simple to state: time itself does not need to end for the universe to become unrecognizable. A clock can keep ticking even when there is almost nothing left to count. When that fact is placed beside redshift, structure, temperature, and time, this is the hardest part of endless darkness. The universe becomes readable only by combining many kinds of faint evidence. A dark future is not necessarily empty. It is a future where remaining matter and radiation are too cold, too thin, or too separated to rebuild the kind of luminous universe that exists now. A researcher working with this evidence is not seeing the end directly. The future is absent from the frame. What is present is a constraint. The phrase heat death sounds warm, but it means equilibrium, the loss of usable temperature differences. From that constraint, the final condition is colder and emptier than the name suggests. The conclusion remains careful because the measurement is indirect. Darkness here is a measurable condition. There are fewer photons with enough energy to warm surfaces, fewer stars to define skies, fewer collisions dense enough to ignite fusion, and fewer gradients that can power change. It is not a supernatural absence. It is the ordinary consequence of expansion, cooling, and exhaustion carried to an extreme. Every statement about the far future has a boundary around it. The boundary is not only technological, it is physical. We observe from one location, at one time, inside one observable universe, using messengers that have finite speeds and instruments that add noise. The fate of the universe is inferred from a narrow, illuminated slice of a much larger history. Consider this: a telescope can only gather light that reaches it. If expansion carries a galaxy beyond a horizon, no future signal from it can arrive. This is not just another detail for a catalog. The universe may hide its own history from later observers, and that single fact becomes part of the larger attempt to understand whether the universe is fading, tearing, or continuing into a darker equilibrium. The limit is not a failure of curiosity, it is part of the structure of the problem. A signal has to travel, an instrument has to receive it, and a model has to interpret it without erasing its uncertainty. In cosmology, knowing where the boundary lies is as important as describing what lies inside it. One part of the evidence is simple to state: the cosmic microwave background is now a full sky relic. In the far future, its wavelength may be stretched beyond practical detection. When that fact is placed beside redshift, structure, temperature, and time, one of the strongest clues to the Big Bang could become inaccessible. The universe becomes readable only by combining many kinds of faint evidence. A later observer may not inherit the same evidence. The sky changes slowly, but expansion changes what can ever be seen. Some records available now may be unreachable in the far future, which means present observations are not only scientific data. They are a temporary opening in cosmic history. A researcher working with this evidence is not seeing the end directly. The future is absent from the frame. What is present is a constraint. Archives matter because the sky changes slowly, and a plate, a FITS file, or a calibrated spectrum can preserve information for later comparison. From that constraint, cosmology is partly a science of keeping traces before they fade. The conclusion remains careful because the measurement is indirect. This is why precision and humility belong together. Error bars are not decoration. They are the measured shape of uncertainty. When the topic is the fate of all structure, a careful answer is stronger than a confident one that has outrun its evidence. The point sounds local. Gravitational waves provide another way to observe the universe. They carry information from merging black holes and neutron stars. In the far future, their sources would also become rarer. Nothing in cosmology stands alone for long. Every reliable statement has to survive contact with the rest of the sky. The limit is not a failure of curiosity. It is part of the structure of the problem. A signal has to travel, an instrument has to receive it, and a model has to interpret it without erasing its uncertainty. In cosmology, knowing where the boundary lies is as important as describing what lies inside it. The physical picture begins here. Neutrinos and cosmic rays are messengers as well. They are difficult to catch because they interact weakly or arrive unpredictably. That picture matters because it shows that even now they show that the universe is not known by light alone. It keeps the question close to matter, radiation, gravity, and time, where an ending can be discussed without pretending the unknown is already solved. A later observer may not inherit the same evidence. The sky changes slowly, but expansion changes what can ever be seen. Some records available now may be unreachable in the far future, which means present observations are not only scientific data, they are a temporary opening in cosmic history. Processed telescope images can be beautiful, but the colors often represent filters, wavelengths, and scientific choices. The physical meaning lies in the data behind the picture. That is how a question as large as the fate of the universe becomes something specific enough to test. A measurement is made, checked against other measurements, and placed inside a model that can succeed or fail. This is why precision and humility belong together. Error bars are not decoration. They are the measured shape of uncertainty. When the topic is the fate of all structure, a careful answer is stronger than a confident one that has outrun its evidence. Consider this. Uncertainty enters through calibration, models, foregrounds, and assumptions. Scientists try to measure those uncertainties instead of ignoring them. This is not just another detail for a catalog. A credible answer includes error bars, and that single fact becomes part of the larger attempt to understand whether the universe is fading, tearing, or continuing into a darker equilibrium. The limit is not a failure of curiosity, it is part of the structure of the problem. A signal has to travel, an instrument has to receive it, and a model has to interpret it without erasing its uncertainty. In cosmology, knowing where the boundary lies is as important as describing what lies inside it. One part of the evidence is simple to state. The future of the universe is extrapolated from a short observed interval. 13.8 billion years is large to us, but small compared with the times under discussion. When that fact is placed beside redshift, structure, temperature, and time, humility is not optional in this subject. The universe becomes readable only by combining many kinds of faint evidence. A later observer may not inherit the same evidence. The sky changes slowly, but expansion changes what can ever be seen. Some records available now may be unreachable in the far future, which means present observations are not only scientific data, they are a temporary opening in cosmic history. A researcher working with this evidence is not seeing the end directly. The future is absent from the frame. What is present is a constraint. Different measurements can disagree slightly, and those disagreements may be systematic error, new physics, or both. From that constraint, cosmology advances by taking them seriously without rushing to conclusions. The conclusion remains careful because the measurement is indirect. This is why precision and humility belong together. Error bars are not decoration. They are the measured shape of uncertainty. When the topic is the fate of all structure, a careful answer is stronger than a confident one that has outrun its evidence. Begin with the plain fact that the end of the universe may be determined by physics not yet understood. Quantum gravity, particle stability, and dark energy all reach beyond complete current theory. The most honest map has blank regions. Nothing in cosmology stands alone for long. Every reliable statement has to survive contact with the rest of the sky. The limit is not a failure of curiosity. It is part of the structure of the problem. A signal has to travel, an instrument has to receive it, and a model has to interpret it without erasing its uncertainty. In cosmology, knowing where the boundary lies is as important as describing what lies inside it. The future becomes clearer when it is placed beside the past. The universe has already changed through phases that no human could survive. Inflation, a hot particle plasma, nucleosynthesis, recombination. The first darkness, the first stars, the first galaxies, the buildup of heavy elements, the rise of planets. The end is another phase problem, not an isolated prophecy. One part of the evidence is simple to state. 1 second after the Big Bang, the universe was a hot particle soup. Minutes later, the first light elements formed. When that fact is placed beside redshift, structure, temperature, and time, this early history matters because the future is tied to the same expansion. The universe becomes readable only by combining many kinds of faint evidence. Seen this way, the present is not the center of cosmic time. It is a bright interval when the universe is old enough to have planets and heavy elements, but young enough that stars still form and distant galaxies can still be seen. That timing shapes every question we can ask, because our evidence comes from living inside this particular chapter. A researcher working with this evidence is not seeing the end directly. The future is absent from the frame. What is present is a constraint. 380,000 years after the beginning, atoms formed and light could travel freely, and that light is now the cosmic microwave background. From that constraint, it is the oldest light we can observe directly. The conclusion remains careful because the measurement is indirect. The past is not just background, it is the testbed for the future. Any model that predicts the end must also explain the beginning, the microwave background, the formation of galaxies, and the structure we see now. A future scenario that breaks the past cannot survive. On its own, the first stars formed after a long dark interval seems like a narrow observation. Their ultraviolet radiation changed the surrounding gas. They began the process of making galaxies visible. Nothing in cosmology stands alone for long. Every reliable statement has to survive contact with the rest of the sky. Cosmic history is not a straight line of increasing familiarity. The universe began in conditions beyond ordinary experience, and may end in conditions just as far from it. The familiar era of stars and planets is a middle interval between two extremes. The physical picture begins here. Galaxies grew by accretion and merger. Dark matter halos gathered gas and stars. That picture matters because it shows that large-scale structure emerged from small initial differences. It keeps the question close to matter, radiation, gravity, and time, where an ending can be discussed without pretending the unknown is already solved. Seen this way, the present is not the center of cosmic time. It is a bright interval when the universe is old enough to have planets and heavy elements, but young enough that stars still form and distant galaxies can still be seen. That timing shapes every question we can ask, because our evidence comes from living inside this particular chapter. The Milky Way formed across billions of years. Its disk, halo, central black hole, and satellite galaxies carry different parts of that history. Our future is embedded in that larger galactic evolution. That is how a question as large as the fate of the universe becomes something specific enough to test. A measurement is made, checked against other measurements, and placed inside a model that can succeed or fail. The past is not just background, it is the test bed for the future. Any model that predicts the end must also explain the beginning, the microwave background, the formation of galaxies, and the structure we see now. A future scenario that breaks the past cannot survive. Consider this. The Sun formed from enriched gas about 4.6 billion years ago. Heavy elements in Earth were made by earlier generations of stars. This is not just another detail for a catalog. Even local life depends on cosmic recycling, and that single fact becomes part of the larger attempt to understand whether the universe is fading, tearing, or continuing into a darker equilibrium. Cosmic history is not a straight line of increasing familiarity. The universe began in conditions beyond ordinary experience, and may end in conditions just as far from it. The familiar era of stars and planets is a middle interval between two extremes. One part of the evidence is simple to state. Several billion years from now, the Milky Way and Andromeda are expected to merge. Their stars are unlikely to collide directly because space within galaxies is vast. When that fact is placed beside redshift, structure, temperature, and time, their gas, dust, and orbits will be rearranged. The universe becomes readable only by combining many kinds of faint evidence. Seen this way, the present is not the center of cosmic time. It is a bright interval when the universe is old enough to have planets and heavy elements, but young enough that stars still form and distant galaxies can still be seen. That timing shapes every question we can ask, because our evidence comes from living inside this particular chapter. A researcher working with this evidence is not seeing the end directly. The future is absent from the frame. What is present is a constraint. After the merger, the local gravitational system remains bound, and it becomes one of the last reachable structures in an accelerating universe. From that constraint, everything beyond it slowly recedes into observational loss. The conclusion remains careful because the measurement is indirect. The past is not just background, it is the testbed for the future. Any model that predicts the end must also explain the beginning, the microwave background, the formation of galaxies, and the structure we see now. A future scenario that breaks the past cannot survive. The chain includes even this: the era of bright galaxies is therefore temporary. It began after the first stars and ends when star formation is exhausted. We live during a luminous middle chapter. Nothing in cosmology stands alone for long. Every reliable statement has to survive contact with the rest of the sky. Cosmic history is not a straight line of increasing familiarity. The universe began in conditions beyond ordinary experience, and may end in conditions just as far from it. The familiar era of stars and planets is a middle interval between two extremes. The physical picture begins here. the far future is not empty at first. It is filled with remnants, radiation, particles, and black holes. That picture matters because it shows that emptiness is approached through attrition rather than immediate disappearance. It keeps the question close to matter: radiation, gravity, and time, where an ending can be discussed without pretending the unknown is already solved. Seen this way, the present is not the center of cosmic time. It is a bright interval when the universe is old enough to have planets and heavy elements, but young enough that stars still form and distant galaxies can still be seen. That timing shapes every question we can ask, because our evidence comes from living inside this particular chapter. The Big Freeze is usually the path that follows from a universe dominated by something like a cosmological constant. In that picture, dark energy does not thicken into a tearing force. It does not turn around and pull everything back. It simply keeps the expansion accelerating, so that distances between unbound galaxy systems grow faster and faster. Gravity still works locally, but the large-scale universe becomes increasingly partitioned into regions that can no longer exchange signals. A useful way to picture this is not to imagine galaxies flying through pre-existing space like sparks from a fire. The better picture is that the metric of space itself changes. Bound systems do not expand because their internal gravity, electromagnetic forces, and other interactions hold them together. The space between unbound systems grows. Over time, that distinction between bound and unbound becomes one of the most important facts in the universe. The Milky Way is not being stretched apart by cosmic expansion. The solar system is not expanding. Earth is not expanding with the Hubble flow. Local systems have their own gravitational and electromagnetic structures. This is why dark energy can dominate the cosmic energy budget without making everyday objects swell. Its effect is seen most clearly across enormous distances, where the accumulated expansion of space becomes measurable. That detail is essential because it separates the Big Freeze from the Big Rip. In the freeze, expansion isolates what is not bound and leaves bound structures to age internally. In the rip, under the phantom energy assumption, even bound structures eventually lose. The difference is not mood. It is the difference between dark energy remaining effectively constant and dark energy growing strong enough to overcome bonds that now easily resist the expansion. When astronomers look at distant supernovae, they are using dying stars to study the fate of everything. A Type 1a supernova is thought to occur when a white dwarf in a binary system reaches conditions that trigger a thermonuclear explosion. These events are not perfectly identical, but their light curves can be standardized. That makes them useful distance indicators, and distance indicators are the foundation of expansion history. The late 1990s supernova results were surprising because distant supernova looked dimmer than expected in a decelerating universe. The simplest interpretation was that expansion had sped up. Since then, the evidence has grown broader. No single observation carries the entire burden. Cosmic microwave background data, galaxy clustering, baryon acoustic oscillations, weak lensing, and supernovae all contribute to a picture in which dark energy is not optional. The name dark energy can mislead if it is heard too literally. It does not mean astronomers have found a dark, glowing substance between galaxies. It means that the equations describing expansion require a component with unusual pressure like behavior. It appears to counteract the attractive effect of gravity on cosmic scales. The word dark means unknown and not directly visible, not magical, not empty, not beyond physics. One candidate is the cosmological constant, often associated with vacuum energy. In equations, it behaves with a pressure that drives accelerated expansion and an energy density that does not dilute as space grows. But when physicists try to connect vacuum energy to quantum field theory in a simple way, the expected value is wildly wrong. The observed value is tiny compared with naive predictions, and that mismatch is one of the deepest problems in theoretical physics. The universe, then, may be governed on its largest scale by a number that is both very small and extremely important. This is a strange situation. A faint term in an equation, almost invisible in the early universe when matter and radiation were dense, becomes dominant only after billions of years of expansion. Dark energy is weak in local life, but decisive in the ultimate architecture of cosmic time. The Big Freeze follows this architecture with a kind of severe patience. Galaxy clusters and groups that are already bound remain as islands. Everything not bound to them recedes. Distant galaxies redshift until their light is stretched beyond detection. The sky visible to any future observer becomes smaller in information even if space itself has not stopped expanding. The universe does not close like a door. The signals simply stop arriving. Imagine a future astronomer living around a long-lived red dwarf inside the merged remnant of the Milky Way and Andromeda. Their telescopes may see stars from their own gravitational island, old globular clusters, brown dwarfs, white dwarfs, perhaps black holes detected by motion or accretion. But the larger universe that we map today might be missing. The evidence for cosmic expansion could be almost erased from the accessible sky. That possibility gives the present a strange scientific privilege. We can see the cosmic microwave background. We can map galaxies across deep time. We can measure acceleration while other galaxy systems are still visible. We live late enough for dark energy to have revealed itself, but early enough for the evidence of a hot dance beginning still to surround us. This does not make humanity central. It makes our era observationally fortunate. The cosmic microwave background is one of the clearest examples. It is ancient light from a time when the universe became transparent, about 380,000 years after the beginning. It now fills the sky with a temperature of only a few Kelvin above absolute zero. It is nearly uniform, but the tiny variations in it are the imprint of early density differences. Those differences became the seeds of galaxies and clusters. As the universe expands, that background light continues to stretch. Its temperature falls. Its wavelength grows. In the far future, it becomes colder and weaker, less like a detectable glow and more like a diluted memory. A civilization beginning too late might not easily discover the same early universe we know. The evidence would still have existed, but it would have passed beyond practical reach. The loss of evidence is one form of cosmic darkness. It is not only the stars that fade, the records fade too. Radiation redshifts. Signals cross horizons. Gravitationally unbound structures become causally unreachable. The universe may continue to contain an enormous amount of information in principle, but no single observer can gather it once expansion has carried it away. In the Big Freeze, the first great visible change is the decline of star formation. Galaxies today are not all equally active. Some are blue and rich with young stars. Some are red and quiet, filled mostly with older stellar populations. The difference is partly the amount of cold gas available. Stars are made from gas, and gas is not infinite. Over time, galaxies consume it, heat it, expel it, or lock it into long-lived objects. Our own Milky Way still forms stars, but not at the rate seen in the most active starburst galaxies. Molecular clouds collapse in regions like the Orion complex, where dust hides new stars from visible light, but infrared telescopes can see through some of the obscuration. The process is local and beautiful, but cosmologically temporary. A galaxy cannot form new stars forever unless fresh cold gas keeps arriving. When galaxies merge, gas can be compressed and star formation can surge. Tidal forces throw streams of stars into space. Central black holes may feed if gas reaches them. But mergers also rearrange and exhaust material. In a universe where distant galaxies become less reachable and gas supplies decline, these spectacular events become less common. Structure does not vanish instantly, it ages. The Sun's own future is an example on a scale close enough to understand. Several billion years from now, It will leave the stable main sequence, expand, and become a red giant. Earth may be engulfed or rendered uninhabitable long before any larger cosmic ending matters locally. After shedding its outer layers, the Sun will leave behind a white dwarf, a hot dense core that slowly cools. That white dwarf is a small preview of the long future. It will no longer fuse hydrogen into helium. It will shine because it retains heat. As ages pass, it will grow dimmer. The universe is not yet old enough for any white dwarf to have become a true black dwarf. Those objects are predictions, not observations, because cooling them requires more time than has existed since the Big Bang. This distinction is important. Astronomy often studies objects that have not yet had time to exist. A black dwarf is not a fantasy object, it is the expected cooled state of a white dwarf if the relevant physics continues as understood. But because none can be observed today, the claim carries the quiet caution of extrapolation. The future is built from known processes extended into unobserved time. Red dwarfs complicate the story because they are so long-lived. The smallest true stars burn their hydrogen slowly and efficiently. They can remain on the main sequence for trillions of years. Long after stars like the Sun have become remnants, red dwarfs may still glow. The universe's last ordinary starlight may come from these small, modest stars, not from the giants that dominate dramatic telescope images. There is something restrained about that ending to the stellar age. The last stars are not the largest. They are not the brightest. They are small, cool, and economical. They survive because they spend their fuel slowly. Their planets, if they have any, would orbit close, in systems shaped by flares, tides, and long-term stability. Around them, the universe beyond the local group grows more difficult to see. Eventually, even red dwarfs run out of usable hydrogen. Stellar fusion, which lit the cosmos after the first dark ages, becomes rare and then effectively absent. The universe enters an era dominated by degenerate matter, white dwarfs, neutron stars, black holes, brown dwarfs, planets, and other remnants. The bright starry universe, the one familiar to human eyes and telescopes, becomes a historical phase. This is why the Big Freeze is sometimes more sobering than a violent end. It does not destroy the universe in a single catastrophe. It lets everything finish what it was already doing. Stars burn. Gas thins. Orbits change. Remnants cool. Black holes wait. Expansion continues. No one process has to be spectacular, because the timescale itself does the work. The long-term dynamics inside old galaxies are subtle. Stars and remnants pass one another at great distances, but over vast times, even weak gravitational encounters accumulate. Some objects gain energy and are ejected into intergalactic space. Others lose energy and drift inward. The galaxy slowly evaporates in a gravitational sense, not by heat, but by the redistribution of orbital energy. A remnant ejected from an old galaxy would not trail fire. It would simply leave, carrying its mass and momentum into a space where other structures are increasingly far away. A black dwarf, a planet, or a neutron star could travel through darkness for times that make the current age of the universe almost irrelevant. It would not need to be observed to be real. It would be matter following gravity. Central black holes would also continue to shape the future. The supermassive black hole in the Milky Way is quiet compared with active quasars, but it is still a deep gravitational object at the galactic center. After the Milky Way and Andromeda merge, their central black holes are expected eventually to combine, releasing gravitational waves. Such events belong to the future of bound structures, even in an accelerating universe. Black holes appear permanent from ordinary timescales, but quantum theory gives them a possible ending. Hawking radiation is extraordinarily weak for astrophysical black holes. A stellar mass black hole is colder than the present cosmic microwave background, so it absorbs more from its environment than it emits until the universe has cooled much further. Only in the far future does evaporation become the dominant story. When black hole evaporation finally matters, the universe has already passed beyond the era of stars. The process is slow because larger black holes have lower temperatures and longer lifetimes. Supermassive black holes last far longer than stellar mass ones. The final release of energy from evaporating black holes would occur after such immense durations that even calling it late almost loses meaning. There are uncertainties here too. Hawking radiation has strong theoretical support, but it has not been observed from an astrophysical black hole. The final stages of evaporation require quantum gravity, a theory that is not complete. So the black hole era is both a prediction from known principles and a reminder that the deepest future touches physics still unfinished. If black holes eventually evaporate, the universe after them becomes even harder to describe in familiar terms. There may be photons, neutrinos, electrons and positrons, perhaps other stable particles, all spread thinly through an expanding space. If protons decay, baryonic matter changes more completely. If protons do not decay, some remnants may persist in altered forms. The far future depends on particle stability as much as on starlight. In this picture, endless darkness is not a sudden curtain. It is what remains when every known engine has finished or become inaccessible. No fresh stars, no bright nebulae, no galaxies linked by visible horizons, no warm background radiation comparable to the one we measure. Only the most diluted traces of a universe that once formed atoms, stars, planets, and observers. Some people hear this and imagine absolute nothingness, but that is not what the science necessarily says. A heat-death universe is not necessarily nothing. It can contain particles and radiation. It can contain space-time. It can contain a low-energy state with almost no usable gradients. The loss is not the existence of stuff, but the ability of that stuff to organize into new luminous complexity. Entropy is the word that points toward this loss. It is often described as disorder, but in cosmic fate, it may be more useful to think of it as the spreading out of energy into forms that cannot easily do work. A hot star beside cold space is a powerful gradient. A universe where everything is nearly the same temperature has far fewer possibilities for change. The early universe, paradoxically, was hot and smooth. Yet it had conditions from which structure could grow, because gravity behaves differently from ordinary gases. Slight density variations became stronger over time. Matter fell into wells. Stars formed. Entropy increased, while complexity also appeared locally. The future heat death is not simply a reversal. It is the continuation of energy spreading and gravitational systems exhausting their opportunities. The Big Rip refuses this slow ending. It says, in effect, that the dark energy term could grow so dominant that waiting for stars to die is unnecessary. The universe would not merely cool while structures remain bound. The structures themselves would be pulled out of causal contact internally. A galaxy would lose coherence. A star would become unbound. Later, perhaps, matter itself would fail. The key parameter is the equation of state, often represented by W, which relates pressure to energy density for dark energy. A cosmological constant has W equal to -1. Phantom energy has a value less than -1. That small-looking difference changes the mathematics of the future. If it remains less than -1 in the right way, the scale factor can diverge in finite time. This is why cosmologists care about decimal places. A small shift in a parameter may decide whether the universe fades forever or reaches a finite time singularity. The number is difficult to measure because dark energy is inferred from how expansion and structure behave across billions of years. Supernovae, baryon acoustic oscillations, weak lensing, and cosmic background data each bring part of the constraint. The Big Rip has a sequence that makes it especially strange. Long before planets or atoms are threatened, distant galaxies disappear beyond horizons. Then galaxy clusters become unbound. Then galaxies themselves cannot hold together. Later, solar systems fail. In the most extreme final interval, stars, planets, molecules, and atoms are torn apart. The order follows binding strength, from weakest structures to strongest. This progression should not be oversold. Current observations do not require a big rip. It is a possible future under a particular class of dark energy models. Many measurements remain consistent with a cosmological constant. The rip matters because it shows how the unknown nature of dark energy can alter the ending completely, not because scientists have confirmed that such an ending is approaching. Phantom energy is also theoretically uncomfortable. It can violate energy conditions that are usually expected in physics. It raises questions about stability and the behavior of fields. That does not automatically make it impossible, but it does mean the scenario carries heavier theoretical baggage than the simpler big freeze. A dramatic future is not scientifically stronger because it is dramatic. A universe that rips would end with a kind of precision catastrophe. The expansion rate would not simply be high, it would become dominant at every scale. The forces that now make atoms, rocks, planets, and stars coherent would lose their ability to define structure. What had been local would no longer be protected from the cosmic behavior of spacetime. Yet even here, the language can mislead. Objects are not being pulled apart by wind from outside. The expansion is not a material blast moving through space. It is the changing scale of space itself, and in the Big Rip version that change becomes stronger than the interactions that once made objects meaningful. The violence is geometric before it is visual. The other possibility, that dark energy evolves without producing a rip, is less cinematic but scientifically important. If its influence weakens, the acceleration could slow. If it changes sign or interacts with other components in some model, more exotic futures become possible. A future Big Crunch is not the standard expectation from current evidence, but evolving dark energy keeps cosmology from becoming a closed book. Recent large-scale surveys have increased the pressure on the simplest story. Measurements from galaxy positions, quasars, supernovae, weak lensing, and the cosmic microwave background can be combined to test whether dark energy has stayed constant. Some analyses have found hints that it may evolve. Hints are not verdicts, but they are exactly the kind of tension that motivates new observations. The Dark Energy Spectroscopic Instrument, mounted on a telescope in Arizona, can collect thousands of spectra at a time. Each spectrum adds a redshift. Each redshift adds a point to a three-dimensional map. The map is not a picture in the ordinary sense. It is a record of where galaxies and quasars appear across time, and it lets scientists compare expansion history with the growth of structure. ESA's Euclid mission is designed to map billions of galaxies and trace dark matter and dark energy through weak lensing and galaxy clustering. NASA's Roman Space Telescope is expected to add wide-field infrared observations with high precision. The Vera C. Rubin Observatory will repeatedly scan the southern sky, catching supernovae, variable objects, and the changing sky with unprecedented scale. Together, these surveys will test whether the present model holds. This is an unusual scientific situation. The fate of the universe may depend on instruments still gathering their first years of data. A mirror, a detector, a fiber positioner, an image pipeline, a calibration field, and a statistical model all become part of the answer. The ultimate future is not being guessed in isolation. It is being negotiated with every new map of the sky. Still, even perfect data would have to be interpreted through theory. Dark energy might be vacuum energy. It might be a dynamic field. It might indicate a modification of gravity on cosmic scales. It might connect to physics not yet imagined clearly. Each option must explain why the universe accelerated when it did, why the observed density is what it is, and why local tests of gravity remain so successful. The universe may be simple in its behavior and difficult in its explanation. A cosmological constant fits much of the data with remarkable economy, but that economy does not tell us why the constant has its measured value. Sometimes, physics advances by replacing a simple description with a deeper one. Sometimes the simple description survives, and the deeper reason remains hidden. The ending, therefore, cannot be separated from humility. The Big Freeze is strongly motivated under the Standard Model. The Big Rip is possible under phantom dark energy. Endless darkness is the long tail of heat death. Other outcomes require changes in assumptions about dark energy, gravity, vacuum stability, or particle physics. The universe is not obligated to choose the scenario with the clearest name. There is also a scale problem in the way human minds meet this question. We evolved to understand seasons, storms, hunger, coastlines, animal movement, and the lifetimes of people. Even the age of a mountain is difficult to feel. The lifetime of a red dwarf is beyond ordinary intuition. The evaporation time of a supermassive black hole is beyond even that. Cosmology asks local brains to think in intervals almost without analogy. One way to keep the scale honest is to return to the instruments. A CCD sensor does not feel awe. It counts charge produced by photons. A radio dish does not imagine the early universe. It measures faint microwave signals. A spectrograph does not know the fate of space-time. It separates light into wavelengths. The scale becomes manageable because each measurement is small, repeatable, and limited. The same is true for simulations. A computer does not contain a universe. It contains equations, numerical approximations, initial conditions, and assumptions about matter, radiation, dark matter, dark energy, and gravity. When a simulation produces filaments and clusters resembling the observed cosmic web, that is evidence that the model captures something real. When it fails, the failure is informative too. Simulations of the far future are even more dependent on assumptions. They can show galaxies merging, stars aging, remnants scattering, and horizons shrinking or expanding under different dark energy models. But the farther they go, the more they lean on physics that has not been directly tested over those times. A good simulation is a disciplined question, not a prophecy. The universe has already passed through darkness once. After the cosmic microwave background was released, before the first stars formed, there was a long interval with no starlight. Hydrogen and helium filled space. Gravity worked slowly on small density variations. Then the first stars ignited, and their radiation changed the gas around them. The universe became luminous, not everywhere at once, but region by region. The far future darkness is different. It is not waiting for the first stars. It comes after the last stars. It is not a beginning before complexity. It is the exhaustion after complexity has had its era. The early dark ages were fertile because gravity still had abundant gas to gather. The late dark era is poor because the useful fuel has been spent, locked away, ejected, or diluted. This difference gives the title its quiet weight. Big Freeze, Big Rip, or Endless Darkness are not three interchangeable moods. They describe different physical outcomes. One is slow cooling under accelerated expansion. One is finite destruction under phantom dark energy. One is the almost unbounded continuation of a cold, low-activity universe after light-making structures have faded. Some versions overlap. The Big Freeze leads naturally into endless darkness if expansion continues and no new physics intervenes. Heat death is the thermodynamic description of the same broad future. The names are human handles for processes too large to hold directly. They help only if we remember what they stand for: expansion, entropy, stellar exhaustion, horizon loss, and uncertain dark energy. The question of whether the universe has an edge is separate from whether it has an ending. The observable universe has a horizon because light has had a finite time to travel, and because space has expanded while it traveled. The whole universe may be much larger than what we can observe, perhaps infinite in extent. The fate we infer applies from the physics inside our observable region and the assumption that the same rules continue. That assumption is powerful and necessary, but it is still an assumption. The cosmic microwave background looks nearly uniform across the sky. Large-scale surveys support a universe that is statistically similar in different directions on large scales. These are reasons to extend the model. They are not permission to claim direct knowledge of regions forever beyond observation. Even the word universe has layers. In practical cosmology, it often means the observable universe, the region from which light has had time to reach us. In theory, it can mean all of space-time. In some speculative frameworks, it can mean one region among others. The end of the universe discussed here is the fate of our cosmic expansion, our matter and radiation, our accessible space-time history. Speculation about multiverses or other regions does not solve the physical question. If other domains exist, they do not change how stars in our universe burn fuel or how dark energy shapes our expansion unless there is a testable connection. A disciplined space mystery remains tied to evidence. The unknown is allowed to remain unknown without being turned into certainty. A future Big Crunch would be a different kind of ending, where expansion reverses and the universe collapses. This was once a natural possibility when the density of matter and curvature were less well constrained. Today, with dark energy driving accelerated expansion, a simple crunch is not favored. To revive it, dark energy would have to change behavior in a major way, or some deeper theory would have to alter the long-term dynamics. If a crunch occurred, distant galaxies would eventually stop receding and begin approaching. The cosmic microwave background would heat as the universe contracted. Structure would be compressed rather than isolated. It is a powerful scenario, but it is not the central expectation of current observations. It belongs in the branching map as a reminder that the future depends on the rules, not on names. Another speculative branch is vacuum decay. In quantum field theory, the vacuum may not be simple nothing. It may be a state with properties. If our vacuum were metastable, a transition to a lower energy state could in principle spread at nearly the speed of light, changing the laws of physics as it went. There is no evidence that such an event is coming. It is a theoretical possibility, not an astronomical forecast. Vacuum decay is rarely useful for a title about Big Freeze and Big Rip because it bypasses ordinary cosmic aging. It does not wait for red dwarfs or black holes. It would be a change in the underlying state of fields. The reason to mention it carefully is not to add drama, but to show that the phrase end of the universe has more than one meaning in physics. Most of the observable evidence still points back to expansion history. The universe was hot and dense. It cooled. Atoms formed. Stars and galaxies emerged. Expansion accelerated after the universe had aged for billions of years. Dark energy now dominates the large-scale behavior. This chain is not complete, but it is strong enough to make the Big Freeze the default path in many presentations. The default path is not the same as a guaranteed path. Science does not need certainty to be meaningful. It needs testable models, stated assumptions, and measurements that can improve or overturn them. A viewer looking at a dark sky may see stillness, but the stillness is deceptive. Under it are spectra, maps, equations, and instruments slowly narrowing what the future can be. The human position in this story is temporary. Not because humans are unimportant in a moral sense, but because stars, galaxies, and expansion do not organize themselves around us. We appear during a bright age, around one middle-aged star, in one galaxy among many. We build telescopes, measure light, and ask what happens long after any familiar landmark is gone. This temporary position gives the question its tension. We cannot wait to see the outcome. We cannot send a spacecraft to the end of time. The most distant probes we have built are still inside the extended reach of the Sun compared with cosmic scales. Voyager's weak radio signals are extraordinary human achievements, but they do not escape the need for inference when the subject is the fate of all space. A spacecraft signal becomes a useful image here. It leaves an antenna as radio waves, crosses the solar system, weakens with distance, and arrives as a faint pattern that has to be pulled from noise. Cosmology is similar in spirit, though the distances are vastly larger. A photon leaves a galaxy, travels through expanding space, and arrives changed. The change is the message. Every future scenario changes that message differently. In the Big Freeze, redshift continues stretching light until distant galaxies fade from view. In the Big Rip, horizons shrink and bound structures eventually cannot send coherent signals across themselves. In a dark energy evolution scenario, the redshift-distance relation may depart subtly from the simplest expectation. Observers look for those differences now, because later may be too late. The cosmic web is one of the most beautiful pieces of evidence because it is large enough to show the universe as a structure rather than a collection of isolated galaxies. Filaments extend across hundreds of millions of light years. Clusters gather at intersections. Voids occupy the spaces between. Dark matter provides the scaffolding, ordinary matter lights parts of it, and dark energy influences how that structure grows with time. In a far future freeze, that web does not remain a reachable network. Regions not gravitationally bound to one another lose causal contact. The web becomes, from any one island, a memory of a time when light could still cross the distances. The universe may still contain those distant structures beyond the horizon, but they no longer participate in the same observational world. This horizon loss is one reason the end of the universe can be lonely without being empty. There may be matter elsewhere. There may be galaxies beyond reach. But for an observer, existence is shaped by what can exchange signals. Accelerated expansion reduces that shared region. The future grows not only colder, but more private, each bound island enclosed by its own increasingly limited sky. That is also why the Big Freeze is not simply about temperature. It is about information, connection, and causality. The cosmic microwave background becomes harder to detect. Other galaxies vanish from view. The large-scale structure becomes inaccessible. The universe does not need to destroy every object to erase the evidence of its own vastness from local observers. If intelligence exists in the far future, its cosmology may be poorer than ours. It might study local stars and remnants in great detail, while lacking the clues that made the Big Bang model obvious to us. It might infer expansion from subtle dynamics, or it might never recover the full story. The universe can become harder to know, even while obeying the same laws. That possibility turns scientific archives into something almost cosmic in their own right. A spectrum stored today, a calibrated map of the microwave sky, a catalog of galaxy redshifts, a gravitational wave strain record, a raw telescope exposure with all its noise preserved. These are records from an era when the universe was still open to observation, in ways it may not always be. The end of the universe is therefore partly a story about data. The Hubble Space Telescope, the James Webb Space Telescope, Chandra, XMM Newton, Planck, Double Map, Gaia, Deci, Euclid, Rubin, Roman, LIGO, Virgo, CAGRA, radio arrays, ground-based optical surveys, and future instruments all contribute pieces. None of them sees the end. Together they constrain the road. Data, however, are not self-explanatory. A cosmic microwave background map has to be cleaned of foregrounds from our galaxy. A supernova sample has to be corrected for dust and population effects. A weak lensing measurement has to account for the intrinsic shapes of galaxies and the behavior of the atmosphere or optics. A redshift survey has to understand selection effects. The future rests on this unglamorous precision. This is why a cautious narrator should not say that scientists know exactly how the universe ends. They do not. The best supported broad future under the Standard Model is continued accelerated expansion and heat death. But the nature of dark energy, the fate of protons, the final behavior of black holes, and the deeper union of gravity with quantum physics all remain incomplete. The uncertainty does not weaken the story. It is the story. A universe that can be measured only through ancient light, faint distortions, and mathematical models should not yield its final answer easily. The fact that scientists can make any disciplined statement about times beyond stars and galaxies is itself remarkable. The fact that the statement remains provisional is what keeps it honest. Suppose the Big Freeze is correct. The Milky Way and Andromeda merge. Star formation flares and then declines. The new galaxy ages. Red dwarfs outlast brighter stars. White dwarfs cool. Neutron stars spin down. Black holes remain. Objects scatter. Horizons empty the sky of other galaxies. Radiation stretches. Time continues. There is no last sunrise for the universe as a whole. Suppose the Big Rip is correct. The distant universe disappears first. Structures lose their boundaries from largest to smallest. The timeline becomes finite. The ending is not after the last star, but before slow stellar exhaustion can finish its work. The universe becomes a place where expansion is not background behavior, but the dominant force at every scale. Suppose dark energy changes in a more complicated way. The acceleration could weaken. A future collapse could become possible in some models. The universe could approach a different state. Its vacuum could behave in a way not captured by current equations. These possibilities are less settled, and some are speculative, but they remind us that the present model is a map rather than the territory itself. Among these branches, endless darkness remains the most patient. It does not require a new violent ingredient. It requires only that stars are finite, gas is finite, useful gradients fade, and expansion prevents the universe from renewing itself as a connected luminous whole. It is not a monster at the end of time. It is the long consequence of ordinary processes that are already underway. The night sky hides this because it is full of points of light. The points feel permanent, but many are temporary in different ways. Massive blue stars may live only millions of years. Sun-like stars live billions. Red dwarfs live trillions. White dwarfs shine as they cool. Even galaxies, which appear stable in photographs, are passing configurations of matter under gravity. A long exposure makes the sky richer, not more permanent. More galaxies appear. Fainter structures emerge. Background noise averages down. But the exposure is still looking backward. The more distant the object, the older the light. A telescope looking deep into space is also looking into a universe less aged than the one that exists now at those distant locations, if those locations can even be spoken of in a simple present tense. This backward-looking nature of astronomy is one reason the future has to be modeled. We can observe many stages of cosmic history by looking far away, but we cannot observe stages that have not happened anywhere in our past light cone. No galaxy we see is a galaxy from the black hole era. No telescope frame contains a true black dwarf. No survey directly records the final temperature of heat death. The future is inferred from physical laws tested in the present and the past. Stellar evolution is tested by observing stars of different masses and ages, clusters whose members form together, white dwarfs, supernova remnants, and nucleosynthesis products. Cosmological evolution is tested by redshift surveys, background radiation, and structure growth. The ending is where these tested laws are extended beyond direct sample. Extension is powerful, but not invincible. General relativity has passed difficult tests, from Mercury's orbit to gravitational waves from merging black holes. Quantum theory has passed tests with extraordinary precision. Yet the deep future of black holes asks for both at once. Dark energy asks for a connection between gravity, vacuum, and cosmic acceleration that no complete theory yet provides. That is why black hole evaporation sits near the edge of known physics. Hawking's calculation combines quantum fields with curved spacetime, but not a full theory of quantum gravity. It predicts that black holes radiate thermally and lose mass. For cosmic fate, the essential point is that even black holes may not be eternal. But the exact final act remains beyond confirmed observation. A supermassive black hole in the far future would be almost unimaginably cold. It would not blaze like a quasar unless fuel was falling in. With little gas left, it would sit in a sparse environment, bending paths, holding mass, and very slowly losing energy through a process too faint for any present detector. Its lifetime would dwarf the stellar era. When the last black holes evaporate in the standard heat death picture, the universe is not restored to brightness. There may be brief final emissions relative to the surrounding darkness, but they occur in a cosmos where the ordinary meaning of a sky has vanished. Afterward, what remains is thin radiation and particles spread through expanding space. This is the endless darkness that follows the freeze. It is not dramatic, because drama depends on contrast, and contrast is exactly what the universe is losing. There is no audience required by physics. There is no final announcement. The processes simply become rarer, colder, weaker, and more separated until almost nothing remains that can mark change in a familiar way. The word almost does a lot of work. Physics is careful with absolutes. If a process has a non-zero probability over immense times, rare events may occur. If certain particles are stable, they persist. If space continues expanding, distances continue changing. The far future may never become perfect nothing. It may become a universe where the remaining events are so rare and low energy that time loses most of its practical markers. That possibility raises a quiet question about what it means for the universe to end. Does it end when stars stop forming? When the last star goes dark? When black holes evaporate? When no observer can gather energy to keep records? When entropy approaches its maximum? Or does it not end at all, but continue in a state that no longer resembles the active universe we know? Science can describe processes more clearly than it can satisfy the human desire for a single final scene. The Big Freeze is a process. The Big Rip is a process that may reach a final singularity under certain assumptions. Endless darkness is a condition approached by processes. None of them is a moral conclusion. None of them exists to make the universe meaningful or meaningless. They are physical possibilities. The most remarkable fact may be that evidence from the present can reach so far. A faint supernova in a distant galaxy, a ripple in the microwave background, a small distortion in the shape of a background galaxy, a pattern in galaxy clustering, each is local and finite. Together they speak about the destiny of space-time on scales no human journey can touch. That is the discipline of cosmology. It does not escape the universe to view it from outside. It studies from within. Every telescope, every detector, every model, every human thought is part of the same expanding system being studied. The question of the end is asked by temporary matter inside a temporary bright era, using light that has been traveling since before Earth existed. A final answer should therefore sound provisional. If dark energy is constant, the universe most likely expands forever into a cold, dilute state. If dark energy is phantom, a big rip becomes possible. If dark energy evolves differently, the future changes. If particle physics reveals proton decay or new stable particles, the late universe changes. If quantum gravity alters black hole evaporation, the last eras change. This is not indecision. It is the shape of honest knowledge. Some possibilities are better supported than others. Some are kept alive by gaps in the data. Some are speculative but mathematically interesting. Some may disappear as new observations arrive. The end of the universe is not a settled chapter, it is a frontier drawn at the edge of measurement. For now, the Big Freeze holds the strongest position in the simplest successful model. The universe continues expanding. Dark energy remains close to a cosmological constant. Matter thins. Galaxies beyond the local bound region recede. Star formation fades. The sky darkens over immense time. The future becomes colder, more isolated, and less able to do work. The Big Rip remains the sharp alternative. It waits inside the question of whether dark energy is more extreme than a cosmological constant. A value of W less than -1, if real and persistent, would change the ending from slow exhaustion to finite disruption. Observations continue to test how close dark energy is to that boundary. Endless darkness is the emotional name for the long tail of the freeze, but physically, it is about entropy, horizons, and the absence of luminous engines. It is not empty at first, and perhaps never absolutely empty. It is a universe where the familiar signs of structure have become rare, and where the background of space no longer carries a bright record accessible to local observers. To say that the universe ends in darkness is therefore not to say that darkness wins. Winning is the wrong category. Stars shine because nuclear physics allows them to. Galaxies form because gravity amplifies density differences. Dark energy accelerates expansion because the universe has whatever large-scale component produces that effect. The ending follows from those rules unless deeper rules intervene. Somewhere in the present, a telescope is still collecting light from galaxies that will one day be beyond the reach of any signal. The photons arrive one by one, absorbed in a detector, turned into electrons, counted, calibrated, and stored. They began their journey when the universe was younger. They arrived during a narrow era when their information can still be read. A future astronomer may not have those photons. A future sky may not show the same cosmic abundance. The distant galaxies may have crossed horizons. The microwave background may have stretched into practical invisibility. The large-scale map may have become unrecoverable. That does not make the future less real. It makes the present evidence more precious. The end of the universe, then, is not only ahead of us, it is already implied in the way light arrives, the way stars burn, the way space expands, and the way energy spreads. The future is not visible, but it is entangled with every measurement of the past. A redshifted line in a spectrum is already a clue. A cooling white dwarf is already a clue. A galaxy survey is already a clue. Those clues do not all point with equal strength. They form a hierarchy. Continued expansion is strongly supported. Accelerated expansion is strongly supported. Dark energy's physical nature is not known. The Big Freeze follows from the simplest model. The Big Rip requires a stronger and more speculative dark energy behavior. Endless darkness follows if the freeze continues into the farthest eras. There is a kind of restraint in accepting that answer. It is less dramatic than certainty and more difficult than mystery for its own sake. The universe may not end with a spectacle. It may end by becoming unable to produce spectacles. Or it may end through a rip if the unknown component behaves in an extreme way. Or it may follow a path that future data has only begun to reveal. The practical work continues in the meantime. Fibers are placed on galaxy targets. Supernova alerts are followed up. Weak lensing catalogs are checked for bias. Microwave maps are reanalyzed. Gravitational wave detectors listen for mergers. Space telescopes measure faint galaxies and ancient light. Each effort narrows the possibilities by a little, and the little matters because the question is so large. A single galaxy in an infrared image may be only a smudge. Its light has been stretched by expansion, dimmed by distance, shaped by dust, and filtered through instruments. But when its redshift is known, when its environment is mapped, when it joins millions of other galaxies in a survey, it becomes part of the evidence for how expansion has changed and how the future may unfold. A supernova light curve is similarly small. A point brightens, peaks, fades. The data fit a curve. The curve gives a distance. The distance compared with redshift tests expansion. The death of one star becomes a measurement of cosmic acceleration. This is one of the quiet ironies of the subject. Stellar endings help reveal the possible ending of everything. The cosmic microwave background provides the opposite kind of clue. Not a dying star, but ancient light from the young universe. Its temperature fluctuations show the initial pattern from which structure grew. Its overall geometry helps determine the contents and curvature of the universe. It anchors the past, and the future models must remain consistent with it. Between the supernovae and the background lies the cosmic web mapped by galaxies and quasars. That web shows how matter gathered after recombination, how dark matter shaped halos, how gas cooled into galaxies, how clusters formed, and how dark energy slowed the growth of structure by accelerating expansion. The fate of the universe is therefore written between the earliest light and the latest maps. The current hints that dark energy may evolve are not enough to rewrite the ending on their own. They are a reason to keep measuring. Cosmology has learned to respect tensions without immediately turning them into revolutions. Some disappear with better calibration. Some deepen. Some reveal new physics. The far future depends on which kind this is. Even if the hints fade, the effort will not be wasted. A tighter confirmation of the cosmological constant would strengthen the Big Freeze picture. A measured deviation would open new futures. Either result teaches something. In science, a closed door can be as valuable as an open one if it is closed by evidence rather than assumption. This is the mood the topic deserves. Not panic, not triumph, not a theatrical countdown. The universe is not ending on human time. Its possible futures are not warnings in the ordinary sense. They are consequences of physics at scales that include us, but are not about us. The proper response is attention. Attention means noticing the difference between a star and a galaxy, between a bound system and the Hubble flow, between dark matter and dark energy, between a cold future and a final singularity, between a model and a fact. The names are simple because names have to be. The reality behind them is layered. In the Big Freeze, planets do not all freeze on the same day. Stars do not all vanish together. Galaxies do not suddenly go black. The sequence is staggered over almost incomprehensible durations. Some worlds are destroyed by their suns. Some are ejected. Some drift. Some remnants cool. The universe ages unevenly, but the overall trend is toward less light and less usable energy. In the Big Rip, the staggering is replaced by a more universal clock, though still ordered by scale. Weakly bound structures fail first. Stronger systems fail later. The final stages compress cosmic fate into a narrowing interval. It is a mathematically dramatic future, but its reality depends on a kind of dark energy not yet established. In endless darkness, clocks may still exist in principle, but the events that make clocks meaningful become scarce. A particle crosses a vast emptiness. A photon stretches with the expansion. A remnant travels without a sky of bright neighbors. If time continues without rich change, it becomes hard to describe except through equations. The final human difficulty is that every metaphor breaks. Freezing suggests ice, but the Big Freeze is about heat death and expansion. Ripping suggests fabric, but the Big Rip is about scale factor and binding forces. Darkness suggests an empty room, but endless darkness may contain particles and horizons and space-time. The words point. They do not contain the physics. What remains most reliable is the chain from observation to model. Light arrives. Lines are shifted. Supernovae fade. Galaxies cluster. Background radiation fills the sky. Lensing arcs bend. Gravitational waves pass through detectors. Equations are tested. Parameters are revised. The future is not seen, but it is constrained by everything the universe has already allowed us to measure. That is why the question has no single final image. The last star, the last black hole, the last detectable photon, the last possible observer, the last useful temperature difference, each belongs to a different definition of ending. The universe may not respect our desire to place one scene at the end of the film. It may have eras fading into eras until the word end becomes approximate. Still, an ending can be approximate and real. The age of stars will end. The age of galaxies as luminous systems will end. The era when the cosmic web is observable from within our bound region will end. The era when black holes dominate may end. The era of usable energy may approach a limit. These are not guesses from mood. They are consequences from known physics, with uncertainties honestly attached. The title asks whether the universe will end by big freeze, big rip, or endless darkness. The best current answer is that the big freeze and endless darkness are closely related and strongly favored under the simplest successful model, while the big rip remains a serious but more speculative branch if dark energy is phantom. The deeper answer is that dark energy still decides the map. A telescope mirror does not know this. It only gathers what arrives. Tonight, somewhere, ancient light from a galaxy crosses the last few meters into glass, reflects, and falls onto a detector. The image will be processed, the spectrum measured, the redshift added to a catalog. It is a small act against a future in which such light may no longer be reachable. The universe may freeze. It may rip. It may continue into a darkness so long that ordinary endings lose their shape. For now, it is still bright enough to study itself through us, through instruments made of its own matter, under skies filled with light that has not yet faded beyond the horizon. The final answer is not written in one place. It is spread across the afterglow of the beginning, the motion of galaxies, the deaths of stars, the quiet growth of black holes, and the unknown behavior of dark energy. The universe is still sending the evidence. We are still close enough in cosmic time to receive it. The monitor remains lit in the darkened room. A map of galaxies waits on the screen. Some of those galaxies are already so distant that their present light will never reach us. The data we have is a message from an earlier universe, arriving before the long, cold future closes around it. For now, the signal is here. For now, the universe can still be read. There is another way to approach the big freeze, and it begins with the difference between temperature and activity. A universe can be cold in the ordinary sense and still contain events. A molecular cloud at 10 Kelvin can form stars if gravity gathers it. A black hole can be colder than the background and still grow by absorbing radiation. What matters in the far future is not a single temperature reading, but whether gradients remain that can drive organized change. The present universe is full of gradients. Stars are hot and space is cold. Galactic centers are dense and halos are thin. Molecular clouds can collapse while supernova shocks push gas outward. Planets have warm interiors and cold surfaces. Accretion disks convert gravitational energy into radiation. These differences make the universe active. Heat death is the fading of those differences, not the disappearance of every particle. A spiral galaxy today is a machine for making contrast. Its arms gather gas. Dust lanes absorb visible light and glow in infrared. Young stars ionize hydrogen into pink nebulae in processed images. Massive stars die and drive new turbulence. A central black hole may feed or remain quiet. The whole system is uneven, structured, and capable of change because gravity and cooling have created places where energy can flow. In the far future, much of that machinery is gone. Gas that once formed stars has been locked into remnants or expelled. Dust grains are destroyed, incorporated, or scattered. The spiral pattern may have been erased by mergers or internal evolution. The bright blue population of short-lived stars is absent. What remains is older, redder, dimmer, and increasingly dominated by compact objects that do not easily give their energy back to the universe. The Milky Way and Andromeda are approaching one another because local gravity overcomes the general expansion between them. Their future merger is not contradicted by cosmic acceleration. Expansion dominates on very large scales between unbound systems. Inside the local group, gravity still decides the motion. That distinction is one of the simplest ways to avoid misunderstanding the fate of nearby galaxies. When the merger happens, individual stars are unlikely to collide because the distances between stars are enormous compared with stellar sizes. But gravitational orbits will be rearranged. Gas clouds can collide and compress. Star formation may increase for a time. Tidal tails may stretch outward. The central black holes may eventually sink toward one another and merge. It is a local drama inside a universe that, on larger scales, keeps accelerating. After that local drama, the isolation grows. The merged galaxy, sometimes imagined as a future elliptical-like system, remains bound. Other nearby dwarf galaxies may be absorbed over long times, but galaxies outside the bound neighborhood recede toward horizons. The sky becomes less cosmological and more local. The future inhabitants of any surviving world would inherit a universe with a smaller, visible past. That is one reason the cosmic microwave background is so important now. It surrounds us as evidence that the universe was once hot, dense, and opaque. Its photons have traveled since recombination, stretched from visible or infrared light into microwaves by cosmic expansion. A map of its tiny variations is a fossil image, not of galaxies, but of the conditions before galaxies fully existed. In the far future, those photons continue to stretch. They do not disappear in a dramatic way. They become less energetic, longer in wavelength, and harder to separate from other backgrounds or from the limits of instruments. The universe can erase evidence without destroying it absolutely. It can make the evidence so diluted that practical detection becomes nearly impossible. This matters because cosmology is a historical science. It reconstructs events that no one can repeat in a laboratory. The Big Bang cannot be rerun. Dark energy cannot be bottled. Galaxy formation cannot be restarted for comparison. Instead, scientists use relics, populations, and statistics. If the relics fade beyond reach, a later science may be forced to work with fewer witnesses. The same problem appears in the stellar record. Star clusters are valuable because their stars formed at roughly the same time from the same material. By comparing stars of different masses inside a cluster, astronomers test stellar evolution. But in a future where the bright stars are gone and clusters have dispersed, the evidence becomes less accessible. The universe ages, and its own archives become more fragmented. White dwarfs are one archive that persists. Their cooling rates can be used today to estimate ages of stellar populations. In the far future, the coolest white dwarfs would carry information about how long ago their parent stars died. But as they approach black dwarf states, they become extremely difficult to detect. Their history remains physically present, but observationally hidden. A black dwarf, if such an object eventually exists, would be a quiet relic of a former star. It would have the mass of a stellar core compressed into a planetary-sized body, no fusion, little heat, and almost no light. It would move through a galaxy or intergalactic space under gravity. It would not be mysterious because it violates physics. It would be mysterious because it is the final cooled outcome of a once bright star. Neutron stars carry a different kind of memory. They are born in supernovae, with densities so extreme that a teaspoon of their material would have enormous mass if it could be separated and held, which it cannot in any ordinary way. Many begin as pulsars, sweeping beams of radiation through space. Over time, they spin down. Their beams fade or stop crossing observers. The remnant remains, but the signal weakens. Black holes are the deepest archives in one sense and the poorest in another. They preserve mass, spin, and charge in the external description, while hiding the details of what formed them behind horizons. A stellar black hole may have come from a massive star. A supermassive black hole may have grown through accretion and mergers over cosmic history. In the far future, they become the dominant remaining engines of gravity. In the black hole era, ordinary images would be almost meaningless. There would be few luminous disks because little gas remains to feed the holes. Without infalling matter, a black hole is not a bright object. It is detected by gravity, by motion, by lensing, or by the radiation predicted to leak from its horizon over immense times. The darkness is not an aesthetic choice. It is what a black hole without fuel looks like. Hawking radiation gives the black hole era a possible ending, but one written on timescales far beyond stellar evolution. The temperature of a black hole is inversely related to its mass. Small black holes are hotter. Large black holes are colder. Astrophysical black holes are so cold that the current cosmic background is warmer than they are. They cannot truly begin shrinking by evaporation until the universe cools below them. Once the background becomes colder, the balance changes. Black holes slowly lose mass. As they lose mass, they become warmer, which makes them radiate faster. The final stages, if the theory holds all the way down, would be brief compared with the long preceding lifetime. But the word brief is relative. The important point is that even the most durable known objects may have a final evolution. The final flash of a black hole should not be described too confidently. The last moments require a theory of quantum gravity. Some ideas suggest remnants, others treat evaporation as complete. Some details depend on particle physics at energies not accessible in ordinary observations. The broad idea that black holes are not perfectly eternal is powerful, but the final microscopic ending remains unresolved. If black holes leave remnants, the dark future changes. If they evaporate completely, it changes another way. If protons decay, matter changes on huge timescales. If protons are absolutely stable, certain relics persist. These questions sound small compared with galaxies, but in the far future small particle properties can decide the inventory of the universe. The universe began with particle physics and may end with particle physics. In the first minutes, protons and neutrons formed light nuclei. Later, atoms formed when electrons could bind to nuclei. Much later, stars forged heavier elements, and supernovae scattered them. In the far future, the stability or instability of the particles themselves may determine what remains after astrophysics has run out of bright fuel. That arc gives the subject a kind of symmetry, though not a perfect one. The early universe was dense, hot, and rapidly changing. The far future is dilute, cold, and slow. The beginning produced conditions for structure. The end disperses structure into less useful forms. Between them lies the stellar era, when matter briefly organized into galaxies, stars, planets, chemistry, and observers. In a Big Rip, this long particle-level ending is replaced by a more direct confrontation between expansion and binding. If phantom energy dominates strongly enough, the universe does not wait for black holes to evaporate. The scale of space changes so violently that the concept of an isolated bound object fails. That is why the Big Rip feels like an ending in the ordinary sense, even though it is highly conditional. Mathematically, the Big Rip can be described by a scale factor that becomes infinite in a finite time. Physically, that statement means distances between unbound points grow without bound as the final time is approached. Bound systems are protected only until the expansion effect at their scale exceeds their binding. The final singularity is not something a telescope would watch from a safe distance, because no safe distance would remain meaningful. The first losses in a Big Rip universe would be subtle from inside any one galaxy. Distant galaxies would disappear as horizons changed. The cosmic context would narrow. Later, the local group or galaxy cluster would fail. Stars would drift free. The night sky, if any observers remained, would lose its structure before local worlds were touched. The end begins as isolation before it becomes destruction. When the process reached a galaxy like the Milky Way, stellar orbits would no longer be stable. The galaxy would not explode like a bomb. It would lose coherence as a gravitational system. Stars that had orbited within a shared halo would no longer belong to a bound structure. Dark matter halos would disperse in the same geometric crisis. The architecture of the galaxy would come apart. Solar systems would last longer because they are more tightly bound. A planet orbiting a star is held by a stronger gravitational relationship than a star orbiting through the outskirts of a galaxy. Only in a later and more extreme phase would expansion overwhelm that bond. the planet would not be struck by a wave. The orbit would cease to be a stable solution under the changing expansion. Objects held together by electromagnetic forces, rocks, planets, molecules, and atoms would resist still longer. That is why the final descriptions of a Big Rip become strange. The same cosmic expansion that once acted mainly between galaxy clusters would have become relevant at scales where it is now utterly negligible. The hierarchy of physics would be overturned by the growing dark energy density. No observation today shows that this is happening. The Big Rip remains a possibility tied to a specific dark energy behavior. Current measurements place strong constraints on W, and many are consistent with -1. But the uncertainties are not zero, and the far future magnifies small differences. A tiny deviation, if real and persistent, can become the difference between fading and tearing. That is why the future surveys matter so much. A better map of baryon acoustic oscillations can refine the expansion history. A larger supernova sample can test distance relationships. Weak lensing can show how structure growth responds to expansion. The cosmic microwave background anchors the early parameters. None of these alone is enough. Together they tighten the allowed behavior of dark energy. Baryon acoustic oscillations are especially useful because they come from a known physical scale. In the early universe, pressure waves moved through the plasma of photons and baryons. When atoms formed and light decoupled, those waves left an imprint in the distribution of matter. Today, that imprint appears as a preferred separation scale in galaxy clustering. It is a ruler carried from the early universe into later maps. Using that ruler at different redshifts, astronomers trace how the universe expanded across time. If the ruler appears larger or smaller than expected under a model, the model must adjust. This is not a visual drama, but it is one of the most powerful ways to test cosmic fate. The future depends on how expansion behaved in the past, and the past left a scale in the galaxy distribution. Weak lensing adds a different clue. The shapes of distant galaxies are distorted by the gravity of matter between them and us. Each distortion is tiny. Individual galaxies have their own shapes, orientations, and imperfections, but across large samples, the statistical pattern reveals the distribution of matter. It shows how structure grew, and growth of structure is slowed by accelerated expansion. Supernovae tell distance. Baryon acoustic oscillations tell scale. Weak lensing tells matter distribution and growth. The cosmic microwave background gives initial conditions. Galaxy clusters add another test. Redshift space distortions reveal motion under gravity. The strength of the cosmological model comes from making these different probes agree well enough to describe one universe. If they do not agree, the disagreement has to be understood. It may come from dust around supernovae. It may come from galaxy evolution. It may come from calibration. It may come from assumptions about neutrino mass or gravity. Or it may point to dark energy changing over time. The work is slow because the universe is not labeled for convenience. That slowness fits the scale of the question. The end of the universe should not be answered by a slogan. Big freeze, big rip, endless darkness, each phrase has to be unpacked until it becomes physics. Otherwise, the words become a kind of mythology. The real universe is stranger and more restrained. Numbers, fields, remnants, horizons, and the stubborn absence of complete certainty. If the freeze is right, most of the future is not spectacular. It is dimming. It is waiting. It is small changes over enormous intervals. But the absence of spectacle does not make it less profound. A universe does not have to explode to become unrecognizable. It only has to continue expanding while its engines exhaust their fuel. The idea of endless darkness also changes how the present looks. The bright stars become temporary fires. Spiral arms become temporary structures. The cosmic web becomes a reachable pattern only for a limited era. The microwave background becomes a fading message. The fact that the sky is full of evidence now is not guaranteed by the universe forever. The night sky seen by unaided eyes is only a shallow layer of this evidence. A few thousand stars, a pale Milky Way band under dark conditions, perhaps Andromeda as a faint blur, planets moving against the background. Telescopes deepen the view, but even the deepest field is still a sample. The observable universe is vast, and still it is bounded by horizons. Every horizon is a statement about limits. The particle horizon marks how far light could have traveled since the beginning. The event horizon in an accelerating universe marks what signals sent now can ever reach us in the future. Black hole horizons mark regions from which light cannot escape to distant observers. The fate of the universe is shaped by horizons at every scale. The event horizon of an accelerating universe is especially important for endless darkness. It means that some events happening now in sufficiently distant regions will never be seen from here, no matter how long anyone waits. In the far future, more of the universe effectively leaves the observable story. Space may be larger, but the accessible universe becomes poorer. This is not because light gets tired in the old discredited sense. It is because space expands while light travels. Photons still move locally at the speed of light, but the distance they must cross can grow in a way that prevents arrival. Redshift is the measurable trace of this expansion, and horizon loss is its far future consequence. A photon emitted from a distant galaxy today may never arrive if the galaxy lies beyond the event horizon. Another photon emitted billions of years ago from the same galaxy may be arriving now. This is why deep images can show us galaxies whose later history is already beyond our reach. We receive the past, while the present and future of that region are inaccessible. The end of the universe, then, is not synchronized for observation. We see different epochs layered across the sky. Nearby stars show relatively recent light. Distant galaxies show ancient light. The cosmic microwave background shows the universe before stars. The far future is not in the sky. It has to be projected from these layers. Projection is not guesswork when it is constrained. The laws of stellar structure explain why massive stars die quickly and small stars last long. General relativity explains how expansion responds to energy density and pressure. Thermodynamics explains why usable energy gradients fade. Quantum field theory in curved space suggests black hole radiation. Each piece has its domain. The uncertainty comes from connecting all domains across impossible durations. A good script on this subject should therefore move between scene and equation without pretending to solve the equation on screen. It should show a telescope mirror, a spectrum, a simulation frame, a microwave map, a supernova remnant, and then return to the fact that the final answer depends on dark energy. The mystery is strongest when it stays attached to what can be measured. In the end, the universe may be less like a story with a final page than a process losing contrast. Pages are human objects. The cosmos has no obligation to offer closure. It may simply continue into states where familiar structures no longer form. Or, under other physics, it may reach a singular boundary. The humility is to say which path is favored and why, without pretending the question is finished. That humility does not make the subject smaller, it makes it larger. A certain answer would close the imagination. An evidence-weighted map keeps the scale intact. The Big Freeze is the leading road under the simplest model. The Big Rip is the road opened by phantom dark energy. Endless darkness is what waits if the freeze is carried far enough. The unknown nature of dark energy is the unresolved signpost between them. The question can be brought back to one ordinary-looking graph. Along one axis is distance or redshift. Along another is brightness, scale, or expansion rate. The points do not form a perfect line because the universe is messy and instruments are imperfect. But the pattern is there. The farther we look, the more we are forced to describe not only where things are, but when their light began traveling and how space changed during the journey. That graph is not a prophecy by itself. It is a record. The prophecy enters when the record is placed inside the equations of cosmology. If the measured expansion is combined with a constant dark energy term, the future opens into accelerated expansion and cooling. If the term changes, the curves bend differently. A future that feels impossible to picture becomes a family of lines extending beyond the last measured point. Astronomers know the danger of extending lines too far. A trend in a small dataset can mislead. A systematic effect can imitate physics. A selection bias can make one kind of object appear more important than it is. This is why modern cosmology depends on overlapping methods. The same universe must be explained by supernovae, the microwave background, galaxy clustering, lensing, and the motions of matter under gravity. The reference frame for all of this is the standard cosmological model, often called lambda CDM. Lambda represents the dark energy term in its simplest form. CDM stands for cold, dark matter. The model is not complete in the sense of explaining what dark matter and dark energy truly are, but it is extraordinarily successful at describing many observations. Its success is the reason the Big Freeze is taken seriously. Under that model, the universe becomes more and more dominated by dark energy as matter dilutes. Ordinary matter and dark matter thin out with expansion because the same amount of matter occupies a larger volume. Radiation thins and also loses energy as wavelengths stretch. A cosmological constant does not dilute in the same way. Over time, it becomes the main term in the expansion, even if it was not dominant in the early universe. This delayed dominance is why the universe could form galaxies before dark energy took over. If accelerated expansion had dominated too early, matter might not have gathered into stars and galaxies as we know them. Gravity needed time to amplify small fluctuations. Gas needed time to fall into halos. Stars needed time to form and die, enriching later generations. The end of the universe is tied to the fact that dark energy became important late. That timing is one of the deepest coincidences in cosmology. We live at an era when matter and dark energy are both important enough to measure their competition. Much earlier, dark energy would have been hard to notice. Much later, matter outside the local bound region would be hidden beyond horizons. The present is not special by decree, but it is special observationally. The coincidence may have a deeper explanation, or it may be connected to selection effects, or it may simply be how the parameters of our universe are. Scientists have proposed many ideas, but none has become the clear final answer. A mystery does not need dramatic language when it is this precise. Why should the component that decides the far future become dominant only after galaxies, stars, and planets had time to exist? That question sits behind the title as much as the endings themselves. Big Freeze, Big Rip, and Endless Darkness are outcomes. Dark energy is the hinge. To understand the hinge, scientists map the expansion not at one moment, but across time. They compare the early universe with the middle universe and the recent universe. They ask whether the same simple term can account for the entire record. If future data show that dark energy is consistent with a cosmological constant to high precision, the Big Freeze becomes more secure. Not absolutely guaranteed, because other unknown physics remains, but secure in the way scientific conclusions become secure, by surviving attempts to break them. If future data show evolution, then the fate question opens again. The universe may still freeze, but the road would no longer be the simplest one. A slowly evolving dark energy field could lead to many futures. It might approach a constant state after all. It might weaken enough that expansion changes character. It might remain accelerated without ripping. It might behave differently in the far future than it did in the past. This is where caution matters most, because the number of mathematical possibilities is larger than the number of observationally supported ones. The Big Rip occupies one clear corner of that wider possibility space. It requires dark energy density to increase with expansion. If that condition is not met, the rip does not occur in the classic form. This is why the scenario is useful, but not dominant. It is a test of the consequences of phantom behavior, not a prediction demanded by current observations. The Big Freeze occupies the quieter center of the map. Its power comes from not needing an additional dramatic turn. Stars already age. Gas already declines. Expansion already accelerates. Horizons already exist. Entropy already increases. Carry those known tendencies forward under the simplest dark energy behavior, and the universe becomes colder, darker, and less connected. Endless darkness is what that quiet center looks like after the familiar objects have finished their luminous lives. It is the late face of the same broad future. The Big Freeze describes the thermodynamic and expansion-driven cooling. Endless darkness describes the observational and astrophysical condition that follows. No bright galaxies beyond reach, no new stars in abundance, no warm background glow, no rich sky of accessible cosmic history. A final image might be a single detector pixel registering a photon from a galaxy that will one day be gone from any possible sky. The photon is not aware of its significance. It is absorbed, counted, and added to an array. But in that count is the whole method of cosmology. The universe sends fragments. We build meaning by gathering enough fragments that a pattern survives. Perhaps that is the most honest way to leave the question. Not with certainty beyond the evidence, and not with darkness used as decoration, but with a physical universe still measurable in the present. Stars are burning now. Galaxies are receding now. Dark energy is shaping expansion now. The end, whatever form it takes, is not separate from those facts. It is their continuation into times the sky has not yet shown us. The Big Freeze also depends on a simple fact about expansion that is easy to overlook. As space grows, radiation is stretched. A photon that once had enough energy to be visible can become infrared, then microwave, then radio, and eventually so long in wavelength that detecting it becomes a practical impossibility. This does not require the photon to collide with anything. Expansion itself changes the wavelength while the photon travels. That same stretching affects every ancient background. The cosmic microwave background is the most famous, but the universe also contains backgrounds from stars, dust, galaxies, and high-energy processes. In the far future, all of them are diluted and redshifted. Their energy density falls. Their ability to warm, illuminate, or inform declines. The sky becomes less like a layered record and more like a nearly empty channel. The process is slow enough that no single generation would watch it happen in full. Even across the lifetime of a civilization, the cosmic microwave background would barely change. But cosmology is not limited to human patience. It follows equations and evidence into intervals where small rates accumulate into complete transformations. A tiny cooling per era becomes, over enough eras, the disappearance of a detectable glow. This is why the word forever has to be handled with care. If dark energy behaves as a cosmological constant, expansion continues without a known stopping point. But forever in equations does not mean forever rich with events. A universe can have unending time and still approach a state where almost nothing organized happens. It can continue while its capacity for novelty diminishes. There are models in which rare fluctuations might occur over extreme durations, but those ideas depend on difficult assumptions about horizons, entropy, and quantum states. They are not the main road of the script because the title is anchored in the astrophysical future: freeze, rip, darkness. The responsible path is to keep the focus on what follows from expansion, stellar evolution, and dark energy, and to leave the most speculative recurrences at the edge. The universe's future also depends on whether black holes are the last true engines or merely the last large reservoirs. If a black hole is surrounded by gas, it can shine through accretion, converting gravitational energy into radiation. If it is isolated, it is nearly invisible except through gravity and quantum leakage. The same object can be a brilliant quasar in one era and a dark remnant in another. Quasars belong mostly to a younger universe, when galaxies had more available gas and central black holes could feed rapidly. Their light now arrives from billions of years ago, often from epochs when the universe was forming structure more actively. In the far future, that fuel is scarce. The black holes remain, but the fireworks do not. The end of activity is not the end of mass. A black hole without fuel is a serious object, but not a theatrical one. It bends space-time. It defines an event horizon. It may merge with another black hole if gravity brings them together. Yet, it does not glow on its own in ordinary astrophysical light. The far future is filled with this kind of severity, objects that remain important while becoming difficult or impossible to see. The same could be said of dark matter. It may continue to make up halos and influence motion long after the stars inside those halos have faded. If dark matter particles are stable, they may persist into the far future. If they annihilate or decay through rare processes, the future changes. Because dark matter's particle nature is unknown, another deep uncertainty sits beneath the visible story. The ending of the universe is therefore a stack of unknowns arranged beneath known trends. Stars age, that is known. Gas is finite, that is known. Expansion accelerates, that is strongly supported. Dark energy's nature is unknown. Proton stability is unknown. The full quantum behavior of black holes is unknown. Each layer changes how far the script can speak with confidence. That layered confidence should be audible in the narration. Some sentences can be direct: massive stars die quickly, white dwarfs cool, cosmic expansion stretches light. Other sentences need caution. Dark energy may evolve. Black holes should evaporate under Hawking's theory. Protons may or may not decay. A trustworthy account does not flatten all statements into the same level of certainty. If the universe continues into endless darkness, the last observers, if any exist, would face practical limits more severe than ours. Energy would be rare. Nearby stars would be gone or dim. Other galaxies would be beyond horizons. The cosmic background would be nearly impossible to detect. Even the act of observation requires free energy, and free energy is exactly what heat death removes. This does not mean consciousness or life can be predicted in detail across the far future. It means that any physical process requiring organized energy must confront the same thermodynamic decline. The universe's fate is not only about objects out there, it is also about whether any process can continue to gather information, store it, and act on it. Heat death is hostile to all such processes because it removes the gradients they require. Seen from the present, the fact that anything can ask the question is temporary and strange. Heavy elements had to be made. A stable star had to form. A rocky planet had to cool. Chemistry had to become complex. Instruments had to be built. Photons from the early universe had to still be available. The question of the end is asked during a brief overlap between cosmic brightness and cosmic intelligence. That overlap should not be turned into a lesson or a claim of importance beyond evidence. It is simply part of the physical situation. The universe is old enough to contain observers and young enough to remain observable on its largest scales. This is the window in which cosmology became possible. Later, if the freeze continues, the window narrows. A final look at the three names shows how human they are. Big Freeze gives a temperature image to a thermodynamic process. Big Rip gives a violent image to a mathematical divergence. Endless Darkness gives an observational image to the loss of light and usable energy. The names are useful if they lead back to physics. They become misleading only if the image replaces the mechanism. The mechanism remains the center. Space expands. Matter gravitates. Radiation redshifts. Stars fuse finite fuel. Galaxies consume gas. Black holes store mass behind horizons. Dark energy accelerates the large-scale expansion. Unknown physics may alter the distant outcome. Everything else is an attempt to make those statements visible enough to follow. At the edge of the question, there is no need to pretend the universe has spoken its final word. It has given enough evidence to favor a long freeze under the simplest model. It has left enough uncertainty to keep the Big Rip and other branches scientifically alive. It has shown that darkness is not a mood, but a possible final condition, approach through cooling, dilution, and the loss of reachable light. The unanswered part of the question is not a failure of astronomy, it is a measure of how far the question reaches. A telescope can gather ancient light, but not future light. A detector can record gravitational waves from a merger, but not from the last merger before heat death. A survey can map millions of galaxies, but not the galaxies that have already crossed horizons from which no new signal will come. So the strongest answer is a weighted one. The Big Freeze, followed by a long dark future, is the most natural outcome if dark energy remains close to a cosmological constant and if no new physics intervenes. The Big Rip is possible if dark energy behaves like phantom energy and grows more dominant with expansion. Endless darkness is not a separate catastrophe so much as the late condition of a universe that keeps expanding after its stars have finished. That weighted answer may change. Better measurements may tighten the case for a constant dark energy. They may reveal evolution. They may expose systematic errors in older assumptions. They may show that the simple model survives again. The universe will not hurry to match a title, and science should not hurry ahead of the evidence. The future remains vast, but the map is not blank. The last line of evidence is still arriving. It comes as old light, stretched wavelengths, faint lensing, cooling stars, and the continued motion of galaxies. It does not give a final certainty, but it gives enough to say that the most likely end is not sudden. It is a long fading, unless dark energy turns out to be stranger than it currently appears. The answer is therefore not a single door at the end of time. It is a set of doors, some wider than others, arranged by evidence. The widest door today leads toward continued expansion, cooling, and eventual darkness. Another opens only if dark energy strengthens in the phantom way. Others remain narrow because they require physics that has not yet been established. For now, the universe is still in the bright interval where the question can be asked with evidence around it. Stars still form. Supernovae still mark distances. Galaxies still fill survey maps. The cosmic microwave background still surrounds the sky. The final darkness, if it comes, has not yet taken away the clues. The signal is still here, faint but measurable. And for a universe moving towards silence, that is enough to keep the investigation open. Every careful new measurement adds a little more shape to that answer, even when the answer remains larger than the instruments that seek it. On the screen, the galaxy map remains still, though every point in it belongs to a universe in motion. Some of the light has crossed billions of years to reach the detector. Some of the galaxies that sent it are already moving toward a future from which no later signal will ever arrive here. The map is not the end. It is one surviving frame from the age when the end could still be studied. Outside the room, the sky looks unchanged. Stars burn in the Milky Way. The cosmic microwave background passes through every wall, colder than any human sense can feel. Far beyond the local group, space keeps expanding. The universe has not answered completely, but it is still sending evidence. And for now, the evidence is still bright enough to read.